Unmute. Okay. Unmute ചെയ്തോളൂ. നിങ്ങളാണോ unmute ചെയ്യണത്? Okay. Okay, thank you. Okay. Okay, thank you. Thank you.
Good morning, ma'am. Am I supposed to share my screen? Thank you. I'm not able to share my screen. It says the host has disabled screen sharing. I have already sent it yesterday. Okay. Good morning, everyone. My name is Pooja Nayak. I am student of Christ University. Today, I'm going to be talking about adsorption of organic pollutants from aqueous solutions using polypyrrole nickel molybdate composite. As we know that water is the most essential resource for life on Earth, and the levels of water pollution is increasing day by day. One of the most important reasons for the water pollution is the effluents which are released by the industries, which includes acid, nitrates, phosphate, dyes, etc. So they alter the properties of the water and cause toxicity, mutagenicity, etc. There are several methods for the removal of these effluents, which includes physical, chemical, and biological methods. And out of this, adsorption was found to be the most effective method since it requires a very short period of time, does not produce harmful byproducts, and it is a very simple process. Can you please change to the next slide? There are various common adsorbents like activated carbon nanotubes, bioadsorbents, nanoparticles, etc., that are used for the adsorption process. Next slide, please. So for our study, we used polypyrrole and nickel molybdate. Polypyrrole was obtained from oxidative polymerization of pyrrole, and nickel molybdate was obtained from nickel nitrate and ammonium molybdate. So through studies, it was found that pure polypyrrole has a lower adsorption efficiency when compared to its complexes with metals. Hence, it was combined with nickel molybdate using in situ chemical oxidation polymerization. Next slide, please. Yeah. So nickel molybdate was synthesized from nickel nitrate and ammonium molybdate, and this was added to the polymerization mixture of polypyrrole, which include HCl, pyrrole, polyethylene glycol, and dropwise addition of ammonium persulfate to form the polypyrrole nickel molybdate composite. The application studies were done for the adsorption of methylene blue dye along with the catalyst polypyrrole nickel molybdate. So different amount of the catalyst, concentration of dye, temperature, pH, etc. were used to analyze its effect on the adsorption efficiency of the dye. And the adsorption efficiency was analyzed using UV visible spectrophotometer. Next slide, please. So various characterization techniques were performed. First one is the XRD analysis, which shows that the polypyrrole nickel molybdate composite has peaks for both polypyrrole and nickel molybdate, which are indicated in the table. Next slide. Similarly, for FTIR analysis, the bands for both polypyrrole and nickel molybdate indicating a specific functional group was present in the composite. The BET analysis showed that the surface area was 201.41, indicating a large surface area, which helps in better adsorption of cationic dyes. Similarly, pore volume was 0.22 cc per gram. Next slide, please. Next slide, please. The DLS and zeta potential were analyzed. So DLS was used to study the particle size. So pure polypyrrole had a particle size of 363, and the polypyrrole nickel molybdate composite had a particle size which was higher, and it was increased from 363 to 458. And similarly, the zeta potential was analyzed to study the surface charges, and it was more negative from -22.5 to -27.5. More negative zeta potential helps in better adsorption of cationic dyes. Next slide, please. The SEM and TEM images were analyzed. So the first image gives the SEM image of the polypyrrole, which shows spherical polypyrrole molecules. And the second image shows both spherical polypyrrole nickel molybdate, polypyrrole molecules along with rod-shaped nickel molybdate molecules. And image C and D give a better view of the internal structure. Image E indicates the SAED pattern, which indicates that the material is polycrystalline. Next slide, please. Yeah. So the XPS analysis shows that nickel is present in 2p form, molybdenum is present in 3D form, and nitrogen, carbon, and oxygen are present in 1s form. So that gives details about the various chemical constituents present in the composite. Next slide, please. So the given graph indicates that the absorption of methylene blue dye increases with the increase in time, and there is a decrease in the concentration of the methylene blue dye. So absorption is higher as the time increases. Next slide, please. So various applications were done, and first one, different types of dyes were used. So the absorption efficiency was found to be highest for methylene blue dye, and that is why it was used for further studies. As the amount of catalyst increased, there was an increase in the absorption. This was due to availability of more number of active binding sites. Similarly, as the concentration of dye increased, the absorption increased due to more interaction between the dye and the adsorbent. And as pH increased, the adsorption increased and reached a point of saturation. So at lower pH, the H plus ion concentration is high. That disrupts the bond between the dye and the catalyst. That's why adsorption was better at a higher pH. As temperature increases, the adsorption decreases. This is due to the increase in the kinetic energy of the molecules. So that leads to desorption process. Next slide, please. So adsorption isotherm and kinetic studies were done. So kinetic studies showed that the polypyrrole nickel molybdate composite followed pseudo second order kinetics, and hence it indicates that chemisorption takes place for the adsorption process. Adsorption isotherm also were studied, and that indicated that it followed Freundlich isotherm. Next slide, please. Freundlich isotherm, which indicates that the adsorption takes place in multi-layers on heterogeneous sites. Next slide, please. In conclusion, it can be said that the composite was easily synthesized from its precursor by in situ chemical oxidation polymerization. The various characterization techniques confirm the formation of the prepared composite. Adsorption activity increases with the increase in the concentration of the dye, amount of the catalyst, and pH. And adsorption activity was higher at lower temperatures. And Freundlich adsorption isotherm was followed by the composite, and pseudo second order kinetic model was followed for the adsorption process. Thank you.
Hello, Pooja. Good morning.
Good morning, ma'am.
That was a nice presentation, and I have few doubts, or rather clarification required.
Yes, ma'am.
You have prepared a composite of polypyrrole and nickel molybdenate, right?
Yes, ma'am.
And is it a heterogeneous structure, or they are your sample, final sample? You said your XRD contains both.
Yes, ma'am.
Polypyrrole and molybdenum structure components, as well as FDIR also confirms both, right?
Yes, ma'am.
So that means it is it's like a heterogeneous.
Yes, ma'am. Yes. Yes.
And may I know what is the motivation behind using this polypyrrole nickel molybdenate composite?
Yeah. So pristine polypyrrole, the pure polypyrrole, usually helps in adsorption, but it was found that the adsorption was not very high. Similarly, only nickel molybdate also was used in adsorption, but that also didn't have very high adsorption efficiency. So when these two were combined together, the adsorption efficiency reached to almost 98%. So that is why these two components were combined together.
When you come to the application,
yes, ma'am.
When, say, if you are using it for dye degradation applications, will there be any other effects of molybdenate, side effects of molybdenate in the system?
As of now, through our studies, we have not found any side effects.
Have you done any such studies? Or?
On real water sample, we have to do the further studies. As of now, we have just done on the laboratory sample. So that is the scope of our further research, where we'll be talking about, where we'll be doing research on real water samples collected from various lakes which are highly polluted.
Do you expect methylene blue to be present in the lake water, or?
Yes, so methylene blue is a very common dye which is released into the water, and actually there are various other types also of dyes also. So our composite can helps in it helps in absorption of all those kinds of dyes, but it shows higher levels of absorptions for methylene blue.
Okay, fine.
Yes,
Shila ma'am.
Okay, Pooja.
Yes, ma'am.
I would like to clarify some points.
Yes, ma'am.
What are some of the examples of pollutants that can be removed using this polyphenol composite?
So
In-
for as of now,
In
we have
industry
conducted.
or environmental?
As of now, we have worked on specifically dyes, but
Okay.
further we can think of nitrates, phosphates, etc.
Okay, what another question is, what is the advantage of this composite over other ones?
Yes, so when we take other composites, for example, activated carbon, so those do not have very high absorption efficiency, and also they can be expensive to synthesize and the regeneration capacity is less. But our composite, it can be synthesized using very minimal precursors, and it requires a very short period of time for synthesis, and also gives high absorption when
Okay.
compared to the activated carbon.
Okay, okay, Pooja.
Yes, ma'am.
Thank
Thank you, ma'am. Thank you, ma'am.
Okay. Actually, it is seen that host disabled participant screen sharing. Can you change it? Already I have sent it.
Can you hear me?
Yes, ma'am.
Okay, okay.
Is visible now. Ma'am, can I present now?
Yeah, yeah.
Yes.
Okay, good morning to all. My work is spectroscopic characterization of calcium tungstate and European doped calcium tungstate phosphor. Can you move to next slide? Next slide, please. Okay. We all know that phosphor find applications in lighting and display field, and some of the basic requirements needed for a phosphor material include intense emission, good RGB color purity, high thermal stability of luminescence, and low protection cost, etc. And coming to nanophosphors, next slide, please. Coming to nanophosphors, they are nanostructured materials and they emit light under suitable excitation. Usually they appear in powder or film, etc. And some of the advantages of nanophosphors include higher packing density and lesser non-radiative losses, etc. Next slide, please. And the basic composition of an inorganic phosphor means it consists of a crystalline host and activate ions. That is, crystalline host plus activate ions gives the phosphor material. And here, both the host material and activate ions influences the luminescence properties of the phosphor material. And some of the examples of host materials includes oxides, molybdates, phosphates, tungstate, etc. And the examples of activate ions are rare earth ions, bismuth, chromium, etc. Among these, the rare earth ions are of special importance due to its special optical properties. Next slide, please. Among the rare earth ions, it has special luminescence properties since it has sharp emission, and also it is well shielded by the outer, the 4 of electronic levels of rare earth ions are well shielded by the outer 5s2 and 5p6 electrons. Therefore, it has sharp emission, and also the rare earth ions have emissions in the entire spectral range, that is from UV to near IR. For red emission, we can use europium samarium, and for green emission, we can use terbium. For yellow emission, we can use dysprosium. While in the present work, we have selected the host material as tungstate, and we have selected the europium as the activator ion for red emission. Next slide, please. The samples, that is the calcium tungstate and europium doped calcium tungstate phosphor materials, were prepared by simple co-precipitation method. And this is the flowchart of the synthesis procedure here. 0.1 molar aqueous solutions of calcium nitrate and 0.1 molar aqueous solution of sodium tungstate is prepared, and the solutions were stirred well for 30 minutes and they were mixed, and the product obtained were washed with the deionized water and dried it for 70 degrees Celsius. And finally, the samples were calcined at 600 degrees Celsius for 3 hours in furnace, and the samples obtained were grinded for 30 minutes, and the samples obtained, that is the calcium tungstate and europium doped calcium tungstate, were further characterized by using various characterization techniques like XRD and photoluminescence studies. Next slide. Now we can see the X-ray powder diffraction analysis of the prepared samples. Here, the XRD of calcium tungstate and 5% EU doped calcium tungstate is given in the figure. All the peaks of the XRD matches well with the ICD of calcium tungstate, and the crystal system is found to be tetragonal. The particle size, that is crystallized size, calculated from the Bézier equation is found to be in the range 15 to 16 nanometer. These are the main conclusions of X-ray powder diffraction analysis. Next slide, please. Moving to photoluminescence studies, first we see the photoluminescence analysis of calcium tungstate phosphor. First figure is the excitation spectrum, and second figure is the emission spectrum. When we look into the excitation spectrum, it is recorded on monitoring the 420 nanometer emission of the tungstate group. Here we can see a broad excitation band. This broad excitation band is assigned to the charge transfer, metal charge transfer band of tungstate group. And also we have recorded the emission spectrum on exciting the sample at 256 nanometer. Here we can see a broad emission spectrum and it is centered around 420 nanometer. Here we have concluded the excitation and emission spectrum of calcium tungstate phosphor. Next slide, please. And coming to the photoluminescence studies of europium doped calcium tungstate nanocrystal, we have recorded both the excitation spectrum and emission spectrum. This is the excitation spectrum of the sample. When we look into the excitation spectrum, we can see initially a broad band in the range 200 to 300 nanometer, and it is assigned to the charge transfer transition of tungstate group. After this broad excitation peak, we can see a series of sharp peaks, and all these sharp peaks are assigned to the various peaks of the europium ion, and all the assigned peaks are shown in the figure. Next slide, please. And This is the emission spectrum. We have recorded the emission spectrum under two different excitations. The first excitation, that is, and the first figure is the emission spectrum recorded under host excitation, that is at 256 nanometer. And the second figure is the emission spectrum of the European doped calcium tungsten nanophosphor recorded under the direct excitation of europium ion. Coming to the first figure, we can see that with the excitation of charge transfer band, we can see the emission peaks of europium, which clearly indicates the charge transfer transition, that is energy transfer have been occurred from tungstate group to europium ion, while under direct excitation of europium ion, we can see the characteristics emission peaks of europium ion only. Next slide, please. The above mentioned emission process can be distinguished from this figure, that is the energy transfer diagram. Here we can see the valence band of tungstate group, and this is the conduction band of tungstate group. Under host excitation, that is under 256 nanometer excitation, electrons from the valence band of WO group will get excited to the conduction band. From there, a part of energy is transferred to the europium ion. This europium ions will get de-excited to the 5d0 level. This 5d0 level is the metastable level of europium ion. From there, the ions will get de-excited to the lower 7 levels of europium ion. These are the ground levels of europium ion. From there, we got the emission peaks at 592 nanometer, 616 nanometer, and 652 nanometer. Thus, the prominent render emission is obtained at 616 nanometer, and this can be assigned to the 5d0 7 of 2 transitions of europium ion. While under direct excitation, that is under 350 nanometer, 394 nanometer excitation, the europium ions will get excited to its excited level. From there, it will get de-excited to the 5d0 level. From the 5d0 metastable level, we get the different distinguished characteristic emission peaks of europium ion in the case of direct excitation also. Next slide, please. Okay. Then this all we have discussed some of the spectroscopic analysis of europium doped calcium tungstate, and we all are familiar with the Jude-Ophel theoretical analysis. We all know that Jude-Ophel theoretic analysis is a technique used to describe the spectroscopic parameters of the host material. Usually, the Jude-Ophel theoretical analysis is carried out from the UV visible spectrum, while in the case of europium ion, we can find out it easily from the emission spectrum of europium ion. And in the from the emission spectrum, I have discussed earlier, by using that emission spectrum, I have calculated the spectroscopic parameters of this tungstate group by using the emission spectrum. For that, we have to find out the JO intensity parameters. The JO intensity parameters are denoted as omega 2, omega 4, omega 6. These JO intensity parameters are calculated using this equation. For that, we have used the emission peaks, that is the 5d0 7 of 2, 5d0 7 of 4 transitions of europium ion. These are electric dipole transitions, and we kept the magnetic dipole transition 5d0 7 of 1 as a reference line, and we have evaluated the J intensity parameters, and it is found to be in the range omega 2 greater, omega 4 greater, omega 6. Here we can see the high value of omega 2 is obtained, which indicates that europium ions are situating in the tungstate group, the tungstate host, in an asymmetric site. Next slide, please. And from the evaluated J intensity parameters, that is from the omega parameters, we can find out the different radiative parameters of europium activated calcium tungsten nanocrystal, and we have find out the peak wavelength, transition probability, branching ratio, effective bandwidth, and emission cross section. And we can see from this table the emission, all these parameters, all these radiative parameters are found to be higher for the 5d0 to 7 of 2 transition, and this is matches well with the experimental spectrum also. And we have compared the radiative parameters of this particular transition with the reported other europium doped materials, and from this table we can see that we have obtained almost comparable and high value of all the radiative parameters for this europium doped calcium tungstate with the other reported materials. These are the main conclusions of the theoretical analysis. Okay, next slide, please. And this is the CA diagram. CA diagram actually indicate the emission color of this material. We can see under host excitation, the emission color from the sample lies in the blue region, while for under 394 nanometer excitation, the emission color from the sample lies in the red region. Thus, we can use this phosphor for blue color purpose and for red color purpose under different excitation. Next slide, please. Thus, the major conclusions of the work are the calcium tungstate and European doped calcium tungstate nanocrystals were prepared by simple co-precipitation method, and the average crystalline size obtained was below 20 nanometer. The photoluminescence analysis carried out by recording the excitation emission spectrum of the pure and European doped samples. The geotheoretical analysis shows the high value of emission cross-section and branching ratio for 616 nanometer emission, and it suggests the utility of this material for various display and optical purposes. Thank you.
Okay, Dino. Okay, Dino, that's a good presentation.
Thank you, ma'am.
How can we use this analysis, spectroscopic analysis, to optimize this luminescence efficiency of these materials you have used?
I have carried out the spectroscopic analysis. First one is the luminescence spectrum. From the luminescence spectrum, we can see that the material is excitable under wide excitation can be used. Since the excitation spectrum clearly indicates that under 616 nanometer monitoring excitation, we can see a broad peak initially, and after that a series of sharp peaks were obtained. Thus we can use this material, or we can excite this material under various possible excitation. This is the first conclusion. And after that, we have carried out the spectroscopic quality of this host material by Judoffel theoretical analysis. From there, we can find out the high value of stimulated emission cross-section. Actually, the stimulation emission cross-section indicate the lasing power of a material, and for this particular material, it is high or it is comparable to other reported values, so it is a good material. We can conclude for red emission.
Okay. Can you give some potential applications of these materials?
Okay, it can be used in initially in LED or in white LED purpose. We can use this one since it gives red emission under 394 nanometer excitation. It is NUV excitable, and also it can be used in display purposes and other lighting applications. We can use red LEDs. We can construct using this material, and also we can use it in anti-counterfeiting application. Also, we can use this material since the material is MC only under in UV or UV, so it can be used in anti-counterfeiting purpose also.
Okay, thank you, Dino. Over to Malini.
Yeah, thank you, ma'am. That was a good presentation, and I have a few doubts or rather clarifications. Can you kindly go to your XRD slide?
Okay, so actually the host is...
Yeah, it's okay. It's okay. Okay, I just want to know whether there is any fingerprint of europium in your XRD.
Actually, the both the XRD pattern of calcium tungstate and the europium doped calcium tungstate are similar.
Yeah, so it's exactly similar. There is no
presence of europium.
Yeah,
from XRD, we can confirm the presence of europium.
Okay, it is not possible.
Not possible, but it can be confirmed from the luminescence studies, ma'am.
And regarding the intensity axis of your spectrum, what is the power of that factor? It's very high, it seems.
Yes, it is very high, ma'am. It is of the order of, I think, 10⁵, seems like that. 1 into this.
So you'll be getting that much intense.
Yes, it is intense, ma'am. Since the rare earth ion are from initially, I have said that rare earth ions are sharp and intense emission. And then this is one of the property of the rare earth ion, that is europium ion.
But without europium top sample also, sample without europium also shows intense lines, like.
But intense, but it is not sharp. It is broad. It seems to be broad for calcium tungstate. But for LED purpose and some other purpose, we need sharp emission.
Okay.
So for that purpose, we have doped the europium into this calcium tungstate. We need actually for a luminescent material, we need broad excitation and sharp emission.
Sharp.
This is okay.
And I would also like to know what are the other materials that can be, other than tungstates, what are the materials or common materials that are being used for these applications?
Okay, for lighting purpose or LED purpose, we need high temperature stability materials. For that, we can use tungstate. In addition to tungstate, we can use phosphate, molybdate, etc.
Okay,
Or
tungstates.
titanate. Or titanate.
So the advantage of tungstate is?
Tungstate is it is highly stable. Its temperature stability is very high compared to all other materials, and also it have broad excitation. And this is one of the other advantage of this material.
Okay, fine. Thank you.
Okay, thank you, ma'am.
ഇവരൊക്കെ ലിറ്ററേച്ചർ റിവ്യൂ ഒക്കെ പറയുന്നുണ്ടോ? ഇല്ല. ഒബ്ജക്റ്റീവ് പറയാം. കുറേ പണിയുണ്ട്. ഹൈഡ്രോക്സൈഡ് ഒക്കെ എഴുതി.
Okay, thank you, ma'am. Okay.
Please mute Nirosha. It seems.
Good morning, ma'am.
Good morning, but there is some disturbance. Host, please mute Nirosha James. Who is Nirosha James?
Good morning, ma'am. May I start my presentation?
Yes, please. Yes.
Yes.
Good morning. Is it visible?
Yes, yes.
Yes.
I am Smita Bhaskaran, doing my research under the guidance of Dr. Veena Gopalan at Department of Physics, Vimala College, Thrissur. Here I am presenting my work on a topic, comparative study of structural properties of oleic acid coated metal nanoparticles, cobalt, nickel, and iron by co-precipitation method. Metal nanoparticles find many applications in optoelectronic devices as catalysts and as biosensors. Conventional methods for synthesis of metal nanoparticles are very difficult. So coating the metal nanoparticles is needed for preventing the nanoparticles from oxidation. And in the present work, cobalt, nickel, and iron metal nanoparticles are synthesized by co-precipitation method. Oleic acid is coated on the metal nanoparticles to prevent them from oxidation. Structural properties of coated and uncoated metal nanoparticles are studied using XRD and FTIR. And in the XRD, we observe the formation of graphitic structure on the nickel and iron metal nanoparticles. This is the experimental method to synthesize the metal nanoparticles. The precursors used for the synthesis are metal salts of corresponding metals, that is cobalt sulfide in case of cobalt metal nanoparticle, nickel nitrate in case of nickel metal nanoparticle, ferric chloride in case of iron metal nanoparticle, and sodium borohydride as the reducing agent. Sufficient amount of sodium borohydride is added to the metal salt solution with constant stirring. The solution is turned to black precipitate and it is dried in an oven to get pristine sample. And oleic acid is coated on these metal nanoparticles. For this, the black precipitate is washed several times and oleic acid is added drop by drop. And water is separated from this oleic acid coated sample. The sample is fully coated with the oleic acid, and water is separated from this oleic acid coated sample, and they are dried in an oven. The structural characterization were carried out by XRD analysis and also with the FTIR measurements. And these are the XRD pattern of uncoated metal nanoparticles and the coated metal, oleic acid coated metal nanoparticles. So the crystallite size estimated from the XRD pattern are listed in the table. And in the uncoated metal nanoparticles, it is seen that the XRD pattern shows the prominent peaks of metal oxide phases. And when they are coated with the oleic acid, the XRD pattern shows the prominent peaks of metal oxides, metal nanoparticles rather than the metal oxide peaks. And from the XRD, the presence of graphitic structure in oleic acid coated metal nanoparticles are found out. And nearly 2 theta at 20 degree, a broad prominent peak is present, which is reported to be the reflection from 002 plane of graphite. And the broadness may be due to the formation of sheet-like structures of graphite. The FTIR analysis of oleic acid coated metal nanoparticles are shown in these figures. And in this FTIR spectrum, the bands of metal oxides and also the oleic acid are present. The absorption bands at 580 centimeter inverse was assigned to cobalt oxide stretching vibration mode, and at a 674 centimeter inverse was that of the bridging vibration of cobalt oxygen bonds in CO3O4 phase of the sample in figure A. And in figure B, the presence of metal oxide nickel oxygen bond is evident from the peak at 668 centimeter inverse. And in figure C, the band at 587 centimeter inverse corresponds to the vibration of iron oxide bonds in the structure of Fe3O4. The peaks at 1438 centimeter inverse and 1518 centimeter inverse were attributed to the asymmetric and symmetric stretching vibrations of COO functional group, which confirms that the oleic acid is coated on the surface of the nanoparticles. Then magnetic properties of cobalt metallic particles are studied using VSM. The MH curves of cobalt pristine and oleic acid coated cobalt metal nanoparticles are shown in the figure. And from the MH curves, the magnetic parameters are calculated and it is listed. The saturation magnetization decreases as oleic acid is coated on the metal nanoparticle. And these are the magnetic properties of the cobalt pristine and oleic acid coated cobalt metal particles. And it is concluded that cobalt, nickel, and iron metal nanoparticles are synthesized by chemical co-precipitation method. The synthesized metal particles are coated with the oleic acid to prevent them from oxidation. XRD patterns of oleic acid coated metal nanoparticles showed the presence of metal nanoparticles along with the metallic oxide phases. Cobalt oxide in case of cobalt, nickel oxide in case of nickel, and Fe3O4 in case of iron. The crystallite size estimated from the XRD data is found to be in the range 3 nanometer to 13 nanometer. Then it is found that the broad peak centered at 20 to 21 degree in the XRD is due to the graphitic structures typically obtained from 002 reflections of graphite. Thank you, ma'am.
Okay, Smita. Can you hear me?
Yeah, yes, miss.
Okay. That was a good presentation. I would like to clarify some points. Why do you choose this co-precipitation method for this samples?
The reduction method is very easy technique. This co-precipitation with
What is that? What I am asking, what is the advantage of using this method? There are other methods to prepare this nanoparticles. Okay.
Yeah. Co-precipitation method, it is using this method we get homogeneous nanoparticles, and it is very easy to synthesis this
but the XRD shows, it is in the amorphous side, isn't it?
Yes, miss, that is metal oxide peaks are present in this. It is very difficult to synthesis this metal nanoparticles due to its instability. But using this method, we can easily prepare metal nanoparticles. But some peaks are there. I mean, metal oxide peaks are there in the XRD pattern. But when it is coated with oleic acid, the metal nanoparticles are somewhat protected from the oxidation.
Okay.
Miss.
Over to you, ma'am.
Yeah, thank you, ma'am and Smita, for
Yes,
the
please.
presentation. And I need some clarification. Like in your slide size calculation, as Sheena ma'am has asked, I have the same doubt that your sample contains metal as well as metal oxides.
Yes.
Right?
Yeah.
And FDIR also shows presence of metal oxide.
Yes.
And is there any method to eliminate these metal oxides and isolate the metal nanoparticles from your sample? Have you read anything regarding that, or is there any method?
Actually, we are trying one more method in polystyrene nanocomposites. The metal oxide metals particles are embedded in polystyrene nanocomposites. That is the next method we will be using to protect these metal particles.
From oxidation.
So first we tried with the oleic acid coating, and then next we will do the next method. From the given from the results of this work, then next we have to do the next method. Okay.
And my another doubt is in your XRD from your slide, you have calculated the slide size from your XRD.
Yes,
and what I have seen is that your cobalt sample alone, the coated sample has got lesser the slide size than that of uncoated. Why? Oleic acid coated sample has the slide size less than the pristine sample. Why is it so?
In the uncoated samples, the oxide peaks are dominating.
Okay.
Metal oxide peaks are dominating, and in oleic acid coated samples, the metal particles, the phase of the metal particles are dominating, and they are protected from the oxidation, and that gives only the size of the metal nanoparticles.
But it is the other way in the other two metal particles, metal systems. Right.
In nickel, it is somewhat difficult to protect this nickel metal particles alone.
Okay, and one more point I would like to know is your pristine cobalt and oleic acid cobalt, when you compare it, your Hc value increases when you coat it, but your MS value decreases. That is, fissivity value increases and magnetization value decreases.
Yes, miss. That is decrease in saturation. It is due to the non-magnetic
Component. Okay.
non-magnetic phase of the organic oleic acid. But Hc value, it may be, we think that it may be due to the that cobalt has a high coercivity,
Okay.
and cobalt is protected from the oxidation while when it is coated with oleic acid, and we are getting more coercive values due to that cobalt phase.
Okay, fine. Okay. Thank you.
Okay, thank you, Miss. Thank you.
Good morning. Am I audible? Hello.
Yes.
Yes.
Good morning, all. I'm Aparna N, Assistant Professor, St. Joseph's College, Devagiri. It is reported that about 70 to 20% of water pollution is caused by textile dyeing. Here I am presenting my work on the dark catalytic degradation of textile dyes using thin monosulfide thin films deposited at room temperature. Advanced oxidation processes are an important class of processes for the wastewater treatment. AOPs utilizes highly reactive species like hydroxyl radical produced in situ for the degradation of harmful organic pollutants into non-toxic or less toxic molecules. Dark catalysis is an AOP which can be carried out at the dark at ambient temperature and atmospheric pressure. As dark catalysis do not need any external energy or chemical reagent. It is more advantageous than other advanced oxidation processes. For this method, the catalyst was thin monosulfide thin film. It was prepared using a modified chemical method named as successive layer adsorption and reaction. In this method, the pre-cleaned substrate is alternatively dipped in cationic and anionic precursor solutions. The cationic precursor was stannous chloride dihydrate and anionic precursor was sodium sulfate. The expected reaction is SN2 plus S2 minus giving SNS. The most important factor is that we were able to deposit the thin film at the room temperature itself. It's a very simple, cost-effective method which gives high degree of substrate tolerance, good control over thickness, and only needs low operating temperature. It is very easy to vary the stoichiometry of the thin film in this method. We deposited the thin film by varying the cationic molarity from 0.03 molar to 0.05 molar, where anionic molarity was fixed as 0.03 molar. XRD results confirm the formation of polycrystalline SNS thin film with the orthorhombic crystal structure. There was only the sample prepared with the 0.03 molar cationic solution named as C.03 showed SNS2 peak. All other samples showed SNS peaks only. An increase in SN concentration with the increase in the cationic molarity was observed from the IDAX measurements, and the TGA analysis showed that all the samples are thermally stable. And an increase in the band gap with increase in the cationic molarity can be correlated to the increased thickness due to more amount of material deposited. For example, 0.03 exhibited an extraordinary behavior. It showed a greater band gap of 1.6. It may be due to the presence of SNS2 phase, which is reported to have a higher band gap than the SNS phase. And some images of some samples are shown. XPS result confirmed the formation of SNS. And due to the abundance of constituent elements, cost effectiveness, less toxicity, etc., SNS is suitable for any device fabrication. Its chemical stability, low aqueous solubility, layered structure, inert nature, etc., make it a good catalyst. Aqueous solution of methylene blue with the catalyst was maintained at the dark condition with continuous magnetic stirring. 3 ml of solutions were taken out from the reaction mixture in 15 minutes interval, and UV visible spectrum was recorded. A color decrease in the color with the reaction time is observed, and UV visible spectra absorption peak also decreased with time. A graph of logarithm of C0 by C. C0 is the initial concentration and C is the present concentration. Also, a graph of logarithm of C0 by C with reaction time is a straight line, which indicates that the reaction is following a pseudo first order kinetics. LCMS analysis data before and after of the methylene blue solution, before and after catalytic treatment is shown here. And this is the initial solution, and this is the LCMS graph of solution treated after after catalytic treatment. A decrease in the methylene blue peak and emergence of new peaks indicated that it's not an absorption but the degradation. And the decrease in the catalytic activity in the presence of OH radical scavenger confirmed the role of OH radicals in the degradation process. And to confirm it, we conducted OH radical indicator test using terephthalic acid also. And as it is a heterogeneous catalyst in the form of thin films, it is very easy to recover the catalyst after use from the solution. It is thermally and structurally stable after the use, and the catalyst was able to use without much loss in the degradation efficiency for 5 consecutive trials. And our catalyst was able to degrade both cationic and anionic dyes. We also tried the catalytic efficiency against a commercially available dye of the brand Chakra. It also gave good results. And it is a proposed dye degradation process. First step is the adsorption of dye molecule onto the surface of thin film catalyst. And the SNS is in the SN2 plus state originally, which loses 2 electrons and will become SN4 plus state. These electrons will migrate to the surface of the catalyst, where it will undergo a series of chemical reactions to produce hydroxyl radical. Hydroxyl radicals are highly reactive. It will react the methylene blue molecule, and it will degrade methylene blue molecule into non-toxic or less toxic product. That is the mechanism happening here. And an increase in the catalytic activity due to magnetic stirring is due to the increased contact between catalyst and the dye molecule due to stirring, and also due to the increased amount of dissolved oxygen in the solution due to stirring. We found that there is an optimum concentration of dye for the maximum dye degradation, and an increase in the catalytic activity was exhibited by the samples with more amount of tin. This is due to the increased absorption and the enhancement in the electron exchange. And our material is known as a class of material known as van der Waals epitaxis, where interlayer bonds are very strong and intralayer bonds are weak. So it offers high degree of substrate tolerance. We were able to deposit the thin film on a very flexible substrate also. It is also characterized, and the thin film on the flexible substrate also exhibited good dark catalytic activity. So let me conclude my presentation. The thin monosulfide thin films prepared using successive layer adsorption and reaction method is a highly efficient and stable catalyst for the degradation of textile dyes. The deposition is possible at room temperature and also on flexible substrate. An increase in the catalytic activity was observed with magnetic stirring and in the amount of tin concentration, and there is an optimum concentration of dye for best catalytic performance. Thank you. Hello. Hello.
Hello, Aparna. Can you hear me?
Yeah, ma'am. Okay.
That was okay. That was a good presentation. I would like to clarify some points. You have said that this film is coated on different substrates.
Yeah.
What are the different substrates you have used?
The main deposition was on the glass substrate. It was possible to deposit on glass. Then we tried an OHP sheet, commercially available OHP sheet, a flexible substrate. It is also a thermally sensitive substrate, and we were able to deposit the film on that also.
And how is this activity depends on the substrate? How this
I didn't compare like that, ma'am. I just studied both. The main studies were on the thin film deposited on the glass substrate, and I varied many parameters. I just deposited it on the flexible substrate and also studied that it is also showing dark catalytic activity. I didn't compare the substrate, importance of substrate here.
Okay. You have studied the SEM analysis of the sample, isn't it?
Of only 2 selected samples, ma'am.
Okay. Have you analyzed the effect of this morphology on the study?
No, ma'am.
Okay. Okay. That's all. Over to you, Malini.
Yeah, thank you, ma'am. And Aparna, I also have few doubts or rather clarifications. What could be the thickness of the films, approximate thickness of the films that you have used on glass substrate as well as?
Actually, for this we fabricated comparatively thicker films. It is in the order of 1 micrometer.
What about that on your OHP film?
It is having a comparatively lesser thickness, ma'am.
And what about the shelf life of these films, both on glass as well as flexible films?
Truly speaking, ma'am, after 3 to 4 months, it is degrading, changing color.
That means it is having some reaction with the atmosphere.
Yes.
And you were talking about using that dye solution or something like that. That advantage of this method you were telling about, you can reuse the dye solution. Clear about. Just elaborate.
Pardon, ma'am?
You were telling about you can reuse the dye solution.
Is this slide, ma'am?
No, in your, just go to your, I don't remember the slide number, just slides. Your, maybe by the end of your, yeah, just, in your conclusion. Easy recovery from dye solution after use means your catalyst can be, that's.
A catalyst can be easily recovered.
Okay,
if it is a nano,
I got confused. Yeah. I got
okay.
confused. Yeah, it's okay. And why there is no unit in your absorbance curve, y-axis unit? Your absorption spectrum doesn't show, it doesn't have a unit in the y-axis.
Absorbance.
Your absorption spectrum.
Sorry, ma'am. Actually, it's just intensity, and we are just taking the relative intensity.
No. I was no. You have calculated the band gap, right? I was talking about that curve. This is okay. This you are getting the relative value. Here also you have not absorbance in arbitrary units. Okay, fine. Thank you.
Sorry, ma'am, I will correct it.
Yeah, it's okay. It's okay.
Ma'am, I have some doubt.
Yeah, please.
Hello.
Yeah, please.
Ma'am, what is the degradation efficiency of this film?
The film was able to degrade the dye 98% within 75 minutes.
Okay. Then how can determine the direct band gap material?
Yes, it's a direct. Actually, it have both reported that it also have already direct and indirect band gap material. And I found my material as direct band gap material. It is ranging from 1.48 to 1.88 in this deposition conditions.
Okay, thank you.
Okay, then thank you, Aparna.
Thank you.
Good morning. Am I audible? Am my slide is visible? Now it's visible?
Yes.
Okay. With your permission, let me start my comparative study of optical and dielectric properties of PVA and silver doped PVA. Metal polymer nanocomposites have been identified in academy and industry as a promising candidate in modern science and technology. In contrast to the intrinsic metal oxide or noble metal multilayer, metal polymer nanocomposites are currently being of interest because of their distinctive qualities like outstanding multifunctionality, potential for large-scale manufacturing, a considerable weight reduction compared to metal, and ease of synthesis. Polymer nanocomposites demonstrate superior qualities to pure PVA because they do not require any modification to the processing of polymers. The combination of organic and inorganic material properties of the metal polymer nanocomposites exhibits make them appropriate innovative material to use in various applications like microelectronic devices, sensors, electromagnetic shielding, charge storage capacitor. This study investigates the effect of optical and dielectric properties of PVA with AG doping. The structural characterization of the study were done using XRD analysis, optical characterization performed by FTIR and UV visible spectroscopy. Dielectric measurements were done on both doped and undoped samples using impedance analyzer. In this study, I used the material, polymer material is PVA and the metal as silver. The method of deposition is a simple solution casting method. Why I choose PVA? Due to its superior properties like non-toxicity, low cost, good transparency, biocompatibility. Moreover, it has many applications in industry nowadays. This slide shows the XRD pattern of pure and silver doped PVA. So the red one is the silver doped PVA and black one is PVA. Both have shows the amorphous nature of the prepared samples. This is almost compatible, almost similar to the reported values of PVA. Coming to the optical analysis, the optical absorption spectra of pure PVA and AG doped samples are shown in figure. The characteristic peak of pure PVA is observed at 190 nanometer and 280 nanometer. There is no peak observed in the visible region. And in the case of silver doped PVA, there is an additional peak observed at 424 nanometer. This is the characteristic peak of silver nano. that is due to surface plasmon resonance. We also calculate the band gap of this PVA, pure PVA and silver doped PVA by Doppler. This slide shows the calculated band gap value. The pure PVA shows the band gap of 6 electron volt, whereas in the silver doped samples shows a less energy value, that is 5.42 electron volt. That is, we can conclude that the addition of silver doped sample reduces the band gap to a lower region. This slide shows the FTR spectra of pure PVA and silver doped PVA. The FTR spectra shows the characteristic peaks at the OS stretching band at 3300 centimeter raised to -1, CH stretching vibrations at 2940, and C double bond or asymmetric stretching band at 1731, 1415 at CH to scissor 1251, and CO stretching band, and 832 correspond to CC stretching band. The silver doped PVA film shows an intensity increasing in the peak positions. We also conducted some dielectric studies using this pure PVA and silver doped PVA. The figure A shows the dielectric constant versus low frequency graph, and the B1 shows the dielectric loss versus low frequency graph. From the graph, it is clear that in the case of silver doped PVA, there is a reduction, there is an increase in dielectric constant. That is, pure PVA is a colorless polymer which shows a characteristics value of dielectric constant value, and the silver doped PVA shows a higher value of dielectric constant in low frequency region, and at the high frequency region, this dielectric constant value constant value is reducing. This is explained in the case of conducting metal nanoparticles, and in the case of insulating metals PVA, the dielectric permittivity of the composite material increases as theoretically due to a large conductivity mismatch between these two materials. The PVA and Ag nanoparticle leads to a relaxation process, which can attribute an interfacial in polarization, which contribute this high value of dielectric constant. And we also observe that the dielectric loss decreases with the frequency, and in low frequency region, this decrease is more prominent. We also measured the dielectric loss tangent. It also noticed that the silver doped sample shows a less loss tangent value. We also calculated the complex electric modulus value M star and M double star from the above data. We found that the imaginary part of the dielectric modulus versus low frequency shows an absorption, shows a maximum peak, and as in the case of silver doped samples, this maximum value shifted to low frequency region. We also plotted the four-fold diagram. The nature of the relaxation is predicted by this four-fold diagram. This semicircular depicts the samples are following the Debye model. We also calculated the AC conductivity, and it shows that silver doped samples shows a less conductivity value, or only a slight diminishing in the conductivity value in low frequency region, but in high frequency region, that is almost coinciding. The major conclusion of this work is the PVA and silver doped thin films were successfully deposited by simple solution cast method. The structural characterization of the produced sample were done using XRD analysis, which confirms the material's amorphous nature. The UV visible absorption spectra demonstrate that the indirect band gap decreases with the Ag plus ion doping. In FTR spectra of silver doped samples, the primary functional groups exhibits a greater signal intensity that demonstrate that the carbonyl group can function as an active electron donor when interacting with the Ag plus cation. At room temperature, the frequency dependency of the dielectric characteristics of pure and silver doped samples were studied. The fold diagram illustrates that the relaxation process in PVA film and the silver doped PVA films displays a semicircular plane that represents the debate model. Thank you. No.
Yeah, no.
Okay. Okay, Malini, you can.
Yeah, yeah. I know. I would like to know. You said you have doped the sample with silver, right?
Yeah.
So how did you do that process?
Yeah, actually we are using the solution casting method. We prepare PVA solution and then silver nitrate, so 0.1 millimolar silver nitrate solution is prepared and stir these solutions and transfer to a petri dish and keep it in an hot oven for 48 hours at a temperature of 70 degrees.
So how could you know that it is a silver nanoparticle in that PVA?
We can compare the pure and silver doped sample. It's color itself we can identify the pure PVA is a colorless sample. That's a transparent one. The silver doped samples in yellow color. In addition to we observe and in UV spectra we observe a additional characteristics peaks of 424 nanometer.
That is of silver nanoparticle.
Yeah, that is due to silver nanoparticle. Black one is PVA, only PVA. There is no peak in 424 nanometer. In the case of silver doped samples, we observe that is 424 nanometer.
It's only very small absorbance. Intensity is very, very small. How can you say?
That is why only doped only 0.5 weight percentage silver. Okay. This is only an initial study. We are trying to vary the weight percentage.
You have also said you have drawn call plot for both PVA and silver doped PVA, but your call plot is
this is for pure PVA. In a low frequency region, there is some noise. So that in the case of silver doped PVA, but we can find there is a decrease in value of M star in the case of silver doped.
Okay, and what about this curve is for? You have only one curve here.
This is for pure PVA.
And what about silver doped PVA? You have
that is in the case of that case. There is a in low frequency region. There is some noise due to that interpolarization. That is due to that Maxwell-Walker polarization, interfacial polarization in low frequency region. Okay, so
your conductivity value also shows that with silver doping your conductivity is decreased.
Yeah, conductivity is decreasing in low frequency region only.
Low frequency region means your conductivity value decreasing means towards the DC conductivity value you are getting a decreased value of conductivity. Is it against the normal?
That due to that interfacial polarization. In low frequency region, there is an interfacial polarization. That may be that's why I do this electrical modulus studies. We can eliminate that value in this.
Okay, fine. Yeah, thank you. Ultimate.
Okay, Malini. I have only one question. What is the potential application of this study?
Yeah, the polymer we can use this as a polymer composite in many applications in like this microelectronic devices application, also in charge storage capacity application, sensor application, because PVA is a flexible material. So we can use that in
Okay.
Hello.
Hello.
I have some doubt. If you use only silver nitrate, then what is the mechanism? Actually, the SPR peaks around 420 nanometer. I think it is Ag0 particles.
Yeah.
Okay. Then if you use only silver nitrate, it produce Ag plus.
No, silver nitrate and PBS is acts as a reducing agent in this case.
PV act as reducing agent in this
It's
process.
also. So it acts as a polymer matrix and it also acts as a reducing agent.
Okay, okay.
Any more question?
Okay, fine. I think we can go for the next presentation.
Ma'am, am I audible?
Yes.
Good morning. Myself, Hasina Koikutti, doing a research under the supervision of Professor M. Junaid Busri, Cochin University of Science and Technology. Here I am going to present my work entitled Non-Enzymatic Glucose Oxidation of Nickel Oxide-Rich Nickel-Nickel Oxide Nanocomposite in Alkaline Media Towards Sensing Application. Plan of talk. Let us introduce nickel oxide and nickel. Nickel oxide is a transition metal oxide with a cubic crystal structure. It is a p-type semiconductor with a wide band gap, and exhibits antiferromagnetic ordering at room temperature. And it is well-known electrocatalyst for a wide variety of electrochemical reaction. Nickel is a transition metal. It exhibits ferromagnetic ordering at room temperature, and it is well known for its redox behavior in alkaline media. Nanocomposite. Nanocomposite is a multi-constituent material. It shows intrinsic properties of individual constituents and some additional properties due to the synergy between different constituents. We can tailor the properties of nanocomposite by tuning the properties of individual constituents. Let us introduce electrochemical sensors. Electrochemical sensors are one of the most versatile sensors used for simple, rapid, and economic detection of different analytes and used in wide range of fields such as clinical diagnosis, agriculture, and food technology. Here, in electrochemical sensors, receptors such as enzymes or antibodies immobilized on the electrode surface produce a response which is proportional to the concentration of the analytes absorbed on the modified electrode surface. Here we measure a current response which is proportional to the concentration of the analytes at a fixed voltage. This kind of electrochemical sensors are specifically known as amperometric sensors. The motivation behind our work is conventional glucose sensors are in conventional glucose sensors, enzyme mediates glucose oxidation and produce a detectable current response. As we know, enzymes are affected by various physical conditions such as temperature, humidity, pH, etc. This in turn affected the sensitivity, selectivity, and stability of the glucose sensor. Moreover, nickel-nickel oxide nanocomposite shows good redox property. It is naturally abundant. It is biocompatible and cost-effective. The objective of our work is the study of electrochemical glucose sensing property of nickel oxide-rich nickel-nickel oxide nanocomposite employing cyclic voltammetry and amperometry. These are the characterization tools we used in our present study. Here we synthesize the nickel oxide-rich nickel-nickel oxide nanocomposite by solution combustion technique. The XRD pattern shows the presence of both nickel oxide and nickel phases, and the nickel phase is dominating phase, showing the formation of nickel oxide-rich nickel-nickel oxide nanocomposite. To investigate the electrochemical activity and the glucose sensing ability of our composite, we perform cyclic voltammetric analysis. For this, we use a 3-electrode cell setup with AgCl as reference electrode, nickel oxide-rich nickel-nickel oxide nanocomposite modified glassy carbon electrode as working electrode, and platinum wire as counter electrode in 0.1 molar NaOH electrolyte. Here we perform series over a potential window of 0 to 0.8 volt at a scan rate of 20 millivolt per second. The series of our electrocatalyst, that is nickel oxide-rich nickel oxide GC, shows a well-defined redox peaks showing the electrochemical activity of our composite. And in the presence of 1 millimolar glucose, our analyte CV shows an increase in peak current, showing the glucose sensing ability of our composite. Here we perform series of nickel oxide-rich nickel oxide GCE in 0.1 molar NaOH at different scan rate. The calibration plot of current with square root of scan rate shows a linear increase in both cathodic and anodic peak current with very high correlation coefficient, showing the electrochemical activity of our nickel oxide-rich nickel oxide GCE in 0.1 molar NaOH is diffusion controlled. To investigate about the sensing ability, sensing performance of our composite, we perform chronoamperometry analysis. This graph shows amperometer responses towards successive addition of 0.5 millimolar glucose. From the calibration plot of current with glucose concentration, the linear range of our sensor electrode is 1 millimolar to 11.5 millimolar, and sensitivity of our sensor is 16.66 microampere per millimolar per cm square, and the lower detection limit is 1.02 millimolar. Let us conclude. XRD pattern confirms the formation of nickel oxide-rich nickel oxide nanocomposite. CV measurements reveals the glucose sensing ability of nickel oxide-rich nickel oxide nanocomposite. CV measurements reveals the diffusion controlled electrochemical activity of nickel oxide-rich nickel oxide nanocomposite. Chronoamperometry reveals the glucose sensing ability of nickel oxide-rich nickel oxide nanocomposite over a wide linear range of 1 millimolar to 11.5 millimolar. The sensitivity of the sensor electrode is 16.66 microampere per millimolar per cm square, and lower detection limit is 1.02 millimolar. Reference, acknowledgements. Thank you. Hello.
Okay, Hasina, that was a good presentation. Let me ask some doubts.
Yes,
have you checked the detection limit of this composite for glucose sensing? Can you hear me?
Yes, sir. Yes, detection
have you
limit
checked
for sensing.
the detection
Yes.
limit?
It is not checked. It is calculated from the CV. From this calibration plot.
Okay. Okay. Again, how is the performance of this composite?
Actually, it is
compared to other sensors?
Actually, it is very low, but we can able to increase the performance using this as a base composite base.
Okay. Okay.
Mm.
Hasina, over to you, ma'am.
Yeah, ma'am.
Yes, Hasina.
Yeah.
That was a good presentation, and I need to know what is the advantage of your composite over other detection methods? What do you suggest? What do you suggest the advantage of your system?
Yeah, actually, this nickel oxide nanocomposite if we able to develop this is a transition metal or metal oxide based composite is very cheap and economic, and if we can able to develop it, we can able to develop it as a good sensor.
What are the other sensors being used nowadays?
Nowadays we use enzyme based glucose sensor.
Enzyme based.
Yeah.
Yeah, fine. Just a moment, Hasina. I would also like to know what is this chronoamperometry? What are you doing in that? Just show me that slide.
Yeah. Actually, yes. Yeah. In chronoamperometry analysis, we fix a fixed voltage, and then we measure current response against time.
At a fixed voltage, you are measuring the current.
Yeah.
It's a function of time.
Yeah.
Okay.
During this measurement, we add our analyte continuously to the cell system.
Okay. Okay. Thank you.
Okay.
Yeah, please.
Good morning. Am I audible and my screen is visible?
Yes, yes.
Good morning. I am presenting the nanocrystalline serum tungstate and its dysprosium doped forms with a high NIR reflectance. Serum tungstate nanoparticles find catalytic and pigment applications, which possesses distorted chelate structure crystallized in a monoclinic crystal system with distorted tetrahedral tungstate. It possesses both cerium 3+ and cerium 4+ oxidation states, which causes many oxygen vacancies in the structure. The motivation of the study is to study the optical spectroscopic properties and NIR reflectance of cerium tungstate and its dysprosium doped form to check the suitability to use this material as cool pigments in paints. Chemical precipitation method is used for the material synthesis, and it is followed by calcination at 600 degrees Celsius. The chemicals used are cerium nitrate hexahydrate and dysprosium nitrate hexahydrate as the cation sources and sodium tungstate as the anion sources. Here I have done 6 small percentage of dysprosium, and the samples are named as dy0 and dy6. The characterization studies used are X-ray diffraction, EDS spectroscopy, TEM, FTIR, and UV-Vis NIR reflectance spectroscopy. From the XRD pattern, we can say that only the cerium tungstate phase is C for both the doped and undoped samples. And it confirms with the C2-C phase group confirmed from the ICDD file number 980401920. And the crystalline sizes for the undoped sample is 20.52 nanometers, and for the doped samples, it is slightly decreased as 18.7 nanometers. The EDS analysis confirmed the presence of elements cerium, tungsten, and oxygen in the undoped samples, and additionally dysprosium in the doped sample. This is a transmission electron microscopic images. From the bright field image, it is clear that the particles are agglomerated, and the SID pattern confirms the polycrystalline nature of the sample. The similar observation is seen for the dysprosium doped samples. And here the FTIR spectroscopic patterns. The weak absorption bands are seen at 3,432 and 1,629 centimeter in width, which are the peaks due to adsorbed water molecules due to the symmetric stretching and the symmetric bending modes of hydroxyl groups. And the intense absorption bands at 942, 825, 732, and 686 centimeter inverse peaks are observed for undoped samples, and additionally 455 centimeter inverse peak is observed for dysprosium doped samples. All these absorption bands are due to the tetrahedral tungstate groups. The diffused reflectance spectroscopy, it is seen that we can see high reflectance, nearly about 84% and 80% for the undoped and doped samples. This high NIR reflectance enables these materials to use as cool pigments in paints. The corresponding absorption spectrum and the dot plot of the undoped samples is seen that it shows an absorption edge at the visible end at 500 nanometers, and it has strong absorption peaks in the ultraviolet regions about 350, 302, and 235 nanometers, corresponding to the absorptions of cerium. The absorption at 235 nanometers is only due to cerium 4+, which is the charge transition from oxygen 2- to cerium 4+. And the other transition 350 nanometers is due to cerium 3+. And the superposition of both cerium 3+ and cerium 4+ absorptions takes place from 300 to 350 nanometers. This strong UV absorption helps the material to use as UV filters in coatings and paints. This is the absorption spectrum of the dysprosium doped samples. The visible the absorption edge starts at 510 nanometers, and the band gap is about 2.98 electron volt. As in the previous case, the cerium 3+ and the cerium 4+ absorption peaks are visible here. But additionally, we can say that some other absorption peaks are observed in the NIR region. This NIR region is enlarged, and we can say that for the dysprosium samples only there is 4F transitions taking place. This 4F transition, the schematic diagram is plotted here, and this additional peak seen here is the FF transition of cerium 3+ at 2,275 nanometers, and DD transitions of cerium 3+ at 1,945 nanometers. The dysprosium level transitions are taking place from 6s15/2 to the different levels which are obtained in the NIR region as tabulated in the table. Conclusion. XRD studies confirmed the crystalline monocline chelate structure of undoped and dysprosium doped samples with a slight variation in crystalline sizes. The characteristic vibrations of tetrahedral tungstates are confirmed from FTIR spectra. EDS analysis confirmed the presence of elements present in the sample. The optical absorption spectrum shows 5 absorption transition, that is intraconfigurational FF transition of dysprosium ions in the NIR region, and the intense hypersensitive transition at 1,296 nanometers. The high optical reflectance of more than 80% makes cerium tungstate and dysprosium doped cerium tungstate a potential material as cool pigments in paints. The materials show strong UV absorption properties, hence it can be used as UV filters while applied in coatings and paints. Hence, the strong UV absorption and high NIR reflectance makes cerium tungstate and dysprosium doped cerium tungstate a potential candidate to use as pigments in paints. Thank you.
Okay, Anjali. It's a good presentation. What method is used for this synthesis?
I used
Of this?
chemical. Okay, ma'am. I used chemical precipitation method
Okay.
followed by calcination at the 600 degrees Celsius.
Is there any effect of the synthesis method on the properties?
Actually, from the SEM analysis, we have what spherical particles, and this method is very environment friendly and easy method.
Okay. Over to you, Malini.
Thank you, ma'am, and thank you, Anjali. It was a nice presentation. I just want to know whether your material is a direct band gap or indirect band gap material.
I have plotted the direct band gap at 3.06 electron volts, but it has both the direct and indirect band gap transitions.
But for dysprosium doped sample, your band gap is reduced.
A little reduced.
Okay. And you have also done ADS analysis of the samples. And is the proportion of the various elements are as expected?
This dysprosium amount is seen in the EDS spectra. It is not as expected as in the doping. The stoichiometry is not obtained as expected,
Okay.
but we have got
But still,
the dysprosium peaks.
Yeah. Thank you, Anjali.
Thank you.
Is the presentation is visible? Let us start. I am Bhagilakshmi, MSc Physics student, Government Arts and Science College, Calicut. So, typically, electronics has been defined on three fundamental circuit elements, which are resistors, capacitors, and inductors. So, it was found that there is no element to conduct magnetic flux and charge. So, in 1971, Leon Chua mathematically proposed a fourth fundamental circuit element, which is termed it as a memristor, that is memory plus resistor. So, here we have investigated the effective bottom electrode on the resistance switching of these memory devices, and our device were the TiO2 thin film sandwiched between a top tungsten electrode and the bottom electrode that we are used to wear ITO coated glass and the gold substrate. So what is typically a resistive switching? It is the reversible changes in the electrical resistance of two terminal device that occur upon external electrical bias in a non-volatile fashion. So what is a non-volatility? So let us consider the conventional semiconductor memories that we are using so far, like STAM, DRAM, and flash memories, in which flash memories are non-volatile. That means it can retain the data even if the power is turned off, but other two are volatile. When the speed is taken into account, the flash memories are slower compared to the other two. So a memory to be considered as a future memory or an emerging memory, it should combine all the best features of current memories. So several memories are proposed, like an emerging memory like ferroelectric RAM, magnetic RAM, and phase change RAM, resistive RAM. Among this, resistive RAM has the advantages of high integration density, fast switching speed, and non-volatility. So typical RRAM cell have a capacitor-like structure with a metal insulator metal structure. That means we cannot reproduce the switching properties with a metal configuration or any other configuration, because so that the insulator layer can be switched reversibly between two resistance sets, that is the high resistance state and a low resistance state. So several materials can be used for this purpose, and we have chosen the TiO2 as a material because highly established synthesis routes and we can easily vary the oxidation state, and this is a low cost device. So we have chosen the salt gel spin coating method for the synthesis of thin films. So coming to the experimental part, we have prepared a 0.2 molar solution using titanium isopropoxide as a precursor and ethanol as a solvent. A drop of HCl was used as a stabilizer, and this solution was stirred in a magnetic stirrer for 5 hours and aged for 2 days at room temperature. And this transparent and clear solution obtained was spin coated on substrate using a spin coater at a speed of 3000 rpm and acceleration of 500 rpm per second for 30 seconds. And each layer was annealed at 250 degrees Celsius. And after getting a desired thickness, the whole film was annealed at 250 degrees Celsius for 1 hour. And the electrical characterization was done by CZ-B2902 precision source measure unit and probe station setup. So coming to the result and discussion, for the structural characterization, we have taken the XRD. The figure shows the XRD patterns of film annealed at 250 and 400 degrees Celsius, and the 250 annealed sample was amorphous, and the 400 degree, the crystalline anesthetic peaks were started to appear after annealing at 400 degrees Celsius, and the average crystallite size was calculated using Scherer equation and found to be around 20 nanometer. From the Raman spectra, we confirmed the annotated TiO2. So from optical characterization, we have taken the UV visible transmission spectra, and the figure shows the spectra of film annealed at 250 and 400 degrees Celsius. From the top plot, indirect band gap was calculated and found to be around 3.48 and 3.42 electron volt for the amorphous and crystalline samples. So coming to the main part of the work, that is the IV characteristics, which is a pinched hysteresis loop. This figure shows the IV characteristics of the TiO2 film deposited on ITO coated glass substrate. And as I mentioned earlier, there are two stable resistance states, that is high resistance state and a low resistance state. Usually, a electroforming process, which is a soft breakdown process, is required to bring the device to a low resistance state. So the transition from HRS to LRS is known as the set process, and the transition from LRS to HRS is known as the reset process. And depending upon the polarities of set and reset are same or not, the device can be further classified into unipolar or bipolar device. So this device 1 is typically a bipolar device, and there is no forming processes required for this device. To ensure it, we have fixed the reset voltage around 3 volt and see for different set voltages, and found that the hysteresis window opens only after when the set voltage exceeds some particular value around -4 volts. That means the device have a threshold voltage to switch on the memory properties. So due to that, the threshold voltage is absolutely equal to the forming voltage. The device does not require a forming process. So and also we observe that is a self-contained properties, because usually a device require a current component to secure it from permanent breakdown. So here it shows self-contained properties and have an RO to RO ratio around 10 at a 0.3 voltage, 0.1 volt. And this device, there are typically two types of switching, that is a homogeneous switching and filamentary switching. So this device, one shows a homogeneous switching. That means that can be attributed to the oxygen vacancy induced barrier modulation at the metal oxide interface. Typically, in a low temperature process of filling, there is an accumulation of oxygen vacancies at a TiO2 ITO interface. So, due to the oxidation of the tungsten electrode, there will be a small amount of oxygen vacancies at the top electrode. So, it will produce a Schottky barrier out there. Whenever a negative voltage is applied, due to that oxygen vacancies are positively charged species, it will attract it towards the top electrode, and it will reduce the Schottky barrier and set the devices to on state. Whenever a positive voltage is applied, the oxygen vacancy repel away from the top electrode, and the Schottky barrier increases and the device sets to off state. So this shows the IV characteristics of device 2, that is the TiO2 film deposited on gold substrate, and we got a typical filamentary type switching, that is an abrupt change in the current was observed. So the forming cycle is also given, and we got a reduced operating voltage, and we have to set a current compliance around 10 milliampere, and the R of the R on ratio was found to be around 17 at a rate voltage of 0.1 volt. So it shows a filamentary type switching, that is require a forming process. So during the forming process, there will be a localized conducting channel will be formed to the active layer. That means the conducting channel is typically a McNally phase of TiO2. That means TIN or 2n-1, 2n-1 phase. That means an oxygen deficient phase. So whenever a negative voltage is applied in a device, then the magnetic field will grow towards the top electrode and the conducting channel will be formed and the electron can easily drift through the device and the device set to on state. Whenever a positive voltage applied, the conducting filament will be break and the device set to off state. So further modification of the device will be possible only after detecting the conduction mechanism and how it's related to the observed switching properties. So we have fitted our experimental data to various models proposed like ohmic, SCLC, pool Frenkel and Schottky emission mechanism. And here device 1, we have fitted our data to double logarithmic plot and we found that a linear relationship with a slope equal to 1 at the low field region. That implies that ohmic conduction mechanism is dominating in the low field region for both HRS and NRS. For the high field region, it's shown a nonlinear behavior. So instead, we have fitted to log I versus V raised to half. We got a linear relationship implies that Schottky emission mechanism is dominating in the high field region. We confirm that the barrier modulation is responsive for the switching in the device 1. And for the device 2, we have fitted our data to double logarithmic plot and we got a slope at low field region, we got a slope at equal to 1 and high field region, we got a slope equal to 2. That means SCLC mechanism is dominating in the HRS and for the LRS, it is ohmic. So typically SCLC mechanism is attributed to the trapping and retrapping of electrons in the trap centers. So here the trap centers, oxygen vacancies will act as a trap centers. So this is a conventional mechanism. There are so many papers are published with this mechanism with the filamentary switching. So we have also checked the endurance, that is how the resistance changes according to the number of cycles, and we got a the device 2 was little bit unstable, but when memory properties, when compared to memory properties, device 2 have a better memory property than device 1 because there is a memory loss in the device 1 as the number of cycles are increasing. So we have also observed that the device 1, that is a TiO2 film deposited on ITO substrate, will get formed when the applied voltage is exceeded some particular value. That film get formed and we get a filamentary type switching and the conduction mechanism is also studied and we got a SCLC type mechanism and ohmic mechanism here. And these two devices, I have mentioned a homogeneous switching device and a filamentary type switching device. These two devices have its own application. The homogeneous switching device can be used for the neuromorphic computing. That means we can recreate a human-like memory with these devices because in a human brain, the two neurons are connected by synapse. That means a metal insulator metal structure. So human brain also have a memory loss. The fabricated device 1 shows a memory loss. That means we can reproduce a human-like memory. That is exponential memory and exponential memory loss with these devices. And the device 2 can be used as a typical memory operation. That is the computer memory. That is LRS and HRS can be used as a logic 0 and logic 1. So the conclusions are low temperature solution process TiO2 based resistive memory have been investigated. The investigation of film by XRD, Raman and UV spectroscopic analysis revealed the highly transparent crystalline nature of films, and homogeneous switching exhibited by device 1 is attributed to oxygen vacancy induced barrier modulation at the metal oxide interface and the requisite threshold voltage for switching, and the device shows forming free self-compliance properties. Ohmic and Schottky mechanism was dominated, and the filamentary switching in device 2 is due to the formation and rupture of conducting filaments in the TiO2 layer, and it shows a better memory properties with R to around ratio 17. And ohmic and SCLC mechanism were dominated, and the device 1 gets formed when the applied voltage exceeds some particular value, and it exhibited stable filamentary switching with reduced operating voltage and self-compliance properties. And these are the references, and thank you.
Okay, Bhagilakshmi. That's a good presentation. So you have studied the effect of bottom electrode material on the resistive switching of TiO2 based resistive. Okay. So what are the different bottom electrode material you have used in this study?
For the structural characterization, we have coated, for the XRD analysis, we have coated the TiO2 film on glass substrate. For the Raman, we have used the silicon substrate. For the UV visible transmission, we have used the quartz substrate. For the IV characteristics, since the bottom electrode should be conducting, so we have used the ITO and gold substrate here. And for the in further work, external work, we have used the silver electrodes as well for the purpose.
Okay. And is there any effect of the thickness of this material on the resistive switching?
No.
Thickness of this bottom electrode, whether the thickness of the bottom electrode material affect the switching process?
Thickness of the bottom electrode doesn't affect, but we have started to studying that the thickness of the active layer, how it related to switching, because we have coated with the 3 layers, 5 layers, and 7 layers. The studies is going on how the thickness of the active layer will affect the switching. There is no dependence of bottom electrode thickness on the switching.
Okay. Okay, Bhagyalakshmi. Over to you, Madam.
Thank you, ma'am. And Bhagyalakshmi, that was a very good presentation.
And
I would just like to know what is the thickness of approximate thickness of various layers. If you have a single layer
for
active
the
medium,
single layer of TiO2, it will be around 30 nanometer.
30
So we have
nanometer.
coated around 3 or 4 layer, and it will be 100 nanometer.
Okay. And you were talking about a threshold voltage of 4 volt for device.
Yeah.
And what is that? Is it advantages or what is the typical values that you?
That is forming. Forming process will cause the deformation of active layer because it produces lot of defects in the material, and also it will destruct the electrode material as well. So researcher will looking forward for a device with a no forming device, and several papers will are published with the deposition of an active layer, that is a TI, a pure TI layer between the electrode and the active layer to remove the forming process. Because if the oxygen vacancies are large, concentration of oxygen vacancies are large, the forming voltage will be lower, and if whenever the switching voltage is equal to the forming voltage, the forming process will not be happen. So for that, oxygen vacancy concentration, to increase the oxygen vacancy concentration, several papers are published with the insertion of a TI layer in between. So it is an advantage that the devices are forming free because there is no destruction of the active layer.
Okay, and also regarding, just show me your endurance curve. You have shown a curve which shows endurance of the device.
Yeah.
Is that on the y-axis? It is a resistance.
Resistance.
Okay. With the different cycles of operation, how the resistance changes.
I'm not audible, ma'am.
It's the cycles of operation that you are doing.
We will perform it for a 50 cycle. We can actually do it in the software. How many cycles we have to perform it? So we can use the 50 or 100 cycles. So during that cycle, this is the resistance. This is the high resistance state, and this is the resistance of low resistance state in the IV curve. So we can use the data from the spreadsheet and import to the origin, and we can plot it like this.
My question is whether device 1 and device 2 shows entirely different range of resistances. That is because of your active layer.
Yeah, that is because of the active, because the device 2 get formed. So there will be a conducting path in that device. So the resistance value will decrease because a lot of oxygen vacancies will be formed after the forming process. So the resistance value will be obviously lower in the device 2. But the ratio will be higher for this than this.
Okay. Okay, fine. Thank you.
Thank you, ma'am. Can I stop my presentation?
Yes, Bhagyalakshmi.
Hello? Yes. Trying to share my screen. Can you see my screen? Yeah, I can hear. Yes. Can you please share it? I can't. Thank you. Yes. Can I start?
Yes, please.
Yes, please.
Thank you, ma'am. A very good morning to everyone. Myself, Adhra Mary Johnson, a research scholar at CMS College, Kottayam, working under the supervision of Dr. Arun Kumar KV. And I'll be presenting the work on the title, Color Tunability Studies of Samarium Ions and Silver Nanoparticles, doped Titanosilicate Glass Matrix. Be an introduction followed by the synthesis method, and will be a discussion on the results and the conclusion. As an introduction, I would like to say that my primary aim is to synthesize a multi-component glass to use for multiple applications. The synthesis method uses non-hydrolytic sol-gel method, and we are focusing on incorporating rare earth as well as glass bonding nanoparticles in the colorimetric studies of the prepared samples will be followed. And the rare earth ions that we use is samarium ions. And why we are using the samarium ions? It is due to it is having a very narrow energy level structure, and samarium could be used for display and lighting devices as well as for optical applications. And silicates have emerged as a brilliant host that can serve as extensive luminescent material in lighting and display devices. And the emission wavelength of samarium ion is 568 nanometer, and it usually shows transitions from in the FF, usually rare shows transition in the FF range. And here, for the samarium, it usually emits reddish orange light owing to electronic transitions from 4G 5x2 to the 6H 5x2, 6H 7x2, 6H 9x2, and 6H 11x2. The plasmonic nanoparticles that I incorporated is silver, and silver is having it is an individual metallic particle with unique optical properties due to their size and shape, and it is having a somewhat low cost comparative to gold and platinum nanoparticles. And plasmonic nanoparticles are strong absorbers and scatters of light, and most importantly, they can be used in nanoscience and nanotechnology, and it supports the localized surface plasmon resonance, which gives accounts of the plasmonic nanoparticles. And the structural characterization. Can I have the next slide, please? The synthesis method employed was the non-hydrolytic sol-gel method. As we all know, sol-gel method is a method in which a sol is formed, which is a colloidal suspension of solid particles in a liquid medium and followed by the gelation. And it could be explained in 5 steps. That is a process of hydrolysis and partial condensation of the starting materials, either the precursors, and the gelation of the salt, then aging of the gel form, drying of the aged gel, and calcination at high temperature. And the advantages of the non-hydrolytic effective and easier method, and high purity of the samples, and homogeneity, and lower processing temperature. Either it could be made in the room temperature, and control of the surface and interfaces of the material, and control of the physical and chemical properties of the material. And what we have done is we have took the precursors as TIP for what we do is it is a titanosilicate glass matrix doped with samarium ions as well as silver nanoparticles, and the matrix precursor is TIP, which is the titanium isopropoxide, and TEOS for SiO2, which is tetraethyl orthosilicate. The solvent employed is ethanol, and the catalyst used is nitric acid. And what we do is we take a combination of TEOS and ethanol, TIP and ethanol, and we stir it on a magnetic stirrer. And the rare earth ion samarium and also the silver nanoparticles, they are also mixed with ethanol, and all these are mixed together in the presence of nitric acid as the catalyst, and it will be stirred on a magnetic stirrer, and a liquid form is formed, and we'll be kept it for drying for 3 weeks, and after that we'll be getting a glass matrix, which is then formed silver nanoparticles. The annealing is taking place at 800 degrees Celsius. Can I have the next slide? Can I have the next slide? The structural characterization was done exploring the XRD, TEM, and FTIR. And the XRD analysis of the sample annealed at 750 degrees Celsius is given as that is the red colored peaks show the SiO2 and TiO2 sample docked with samarium ions alone, and the other one is SiO2, TiO2 with samarium and silver. The conformation of the TiO2 nanophase as well as the silver nanoparticle is done in XRD. We are getting peaks at 25.32, 37.79, 75.3, etc. And the broad peak, which is centered at the 21 degree, at the 2 theta value of 21 degree is the peak accounting for the amorphous nature of SiO2. And even though silica is non-crystalline, the broad peak is due to the presence of the short range order. And the characteristic peaks at 25.35 and 62.51 corresponds to the planes of titanium oxide, while the peaks at 37.9 planes of silver nanoparticles respectively. And the crystallite size of the sample was determined using the Debye-Scherrer formula, and it was found to be, the crystallite size was found to be 8 nanometer. Next slide, please. The TEM analysis was done to confirm the presence of the plasmonic nanoparticles of silver, and we got silver nanoparticles as a spherical structure in the TEM analysis, and the crystallite size was found to be 10 nanometer by plotting the histogram analysis. And the next analysis is the FTIR analysis. Can I have the next slide? FTIR analysis was done to confirm the matrix formation, and the glass matrix confirmation is done by the FTIR spectroscopic studies. There were peaks at 3,500 centimeter raised to -1 room temperature sample, which corresponds to the water which came from the ethanol. Our ethanol is only 99% purity, and there is some water content in it, and that is accounted in the FTIR. And the peak at 1,214 centimeter raised to 1. And the main peak, or the characteristic peak, is the peak at 953 centimeter raised to -1, which is the SiO-Ti bond, and the peak at 1,416 corresponds to the stretching vibration at TiO-Ti, and the peak at 860 to 990 centimeter is a typical range of SiO2 and TiO2 matrix. Can I have the next slide? The optical analysis is done by the UV visible spectroscopic analysis. It confirms the presence of the rare earth, which is the samarium, and UV visible analysis gives a confirmation of the presence of the rare earth elements, the samarium ion. Peaks are observed between 250 nanometer to 350 nanometer, and the peak around 330 nanometer is the one among the characteristic peak of the samarium. The peaks are in well agreement. The peaks which is observed for the samarium in the range of 260 to 400 nanometer. Usually, samarium is having peaks in the range of 260 to 400 nanometer. The peaks in the absorption spectra corresponds to the transition from the ground state, that is 6H5 to different higher energy states. And the optical analysis is followed by the photoluminescence spectroscopy. The photoluminescence spectroscopy is a study of photogenerated electron ions show strong reddish orange luminescence in the 550 to 670 nanometer range. The major peaks obtained are at 581 610, 662, 605, 619, and 668. And the spectra obtained to three prominent characteristic emission bands, that is 4G 5x2 to 6H 5x2, corresponding to 581 nanometer, 4G 5x2 to 6H 7x2, that is corresponding to 605 nanometer, and the 4G 5x2 to 6H 9x2, corresponding to 662 nanometer. There exists a variation in the intensity of the emission in the presence of plasmonic nanoparticles of silver, which could be a consequence of the difference in the emission spectra of the samples that is doped with silver is due to the interaction of silver nanoparticles with the samarium ions, and the plasmonic effect of silver is complemented with the presence of titanium. Can I have the next slide, please? The colorimetric analysis, it shows the color tunability in the presence of the plasmonic nanoparticles of silver. As you can see, the chromaticity coordinates are shifted from 0.6 to 0.38 to samarium plus silver, which is 0.6. Corresponding nanoparticles, the psi coordinates can be tuned. Either the color tunability can be done using the plasmonic nanoparticles due to the energy transfer from the silver ions and the samarium ions. Moving to the conclusions, we have a titanosilicate glass matrix which is formed using the non-hydrolytic cost-effective Sol-Gel technique, and XRD analysis confirms the presence of the nanoparticles as well as the TiO2 nanophase, and the calculations done employing the Debye-Scherrer equation found the crystallite size as 8 nanometer, and FTIR studies confirms the presence of SiO-Ti stretching bond, and thereby the confirmation of the titanosilicate glass. Next slide, please. The further confirmation of plasmonic nanoparticle was done by the TEM analysis, which showed the crystallite size to be 8 nanometer, and optical absorption studies of the titanosilicate glass topped with samarium ions gives the confirmation about the presence of samarium ion, and the peak at 330 nanometer is the characteristic peak of samarium, and the PL shows a strong reddish orange emission due to the presence of samarium, and color tunability was accounted, which is presented by using the colorimetric analysis.
Okay, Adira, that is a good presentation, and I just want to please show me your XRD, and you said there are peaks corresponding to silver around 37.
Yes,
With
yes.
and without silver sample, they are almost the same.
Ma'am, actually, TiO2 is also having a peak around 37.
Okay.
Both are having peaks around 37. That's why there is not much difference.
Okay, then what is the fingerprint of silver? You said it is visible from. Yeah.
Yeah, we have other, actually, silver is having a characteristic peak at 37 and 75.
Okay.
In the 75 range, there is a peak, which is the characteristic peak of silver.
Okay. And with and without silver, there is also that red colored pattern. Also, you have a slight small peak like.
One is around
pattern.
Actually it was around 73, and for for silver it is around 75, and titanium we have a peak around 25.35. That is a major peak of titanium.
Okay.
TiO2.
Yeah. And your PL result, and have you done it with and without silver?
We have done it with and without silver, but there was a problem when we were drawing the one bit without silver. So we are working on it actually.
Okay. No, because when you say color tunability with silver,
yeah, I have shown it in the colorimetric analysis. Both in the side plot, I have plotted it.
Okay.
Without silver.
Yeah, fine. So, thank you.
Thank you.
Okay, Adira, that was a good presentation. I would like to know, how do you choose the concentration of this samarium and silver for this color?
Yeah. We have done it in a trial and error method. We have optimized the concentration as 3% of samarium and 3% of silver. We have done in 0.5% and up to 5%. We are facing the quenching process in which the effect is reversed.
Okay. Okay. Whether the size of the nanoparticle affect the color tunability? Did you check that?
No, we have not investigated on that.
Okay.
We are working on it actually. Further, we are doing the dielectric studies as well.
Okay. And the range of colors is as you shown in that diagram.
Yes.
That we cannot obtain from the study. Okay. Beyond that, what do you have to do? If you want to get other colors?
We can change the
Is there a
rare earth ion as
possibility?
well. Yeah, we can change the rare earth, and if we want a white color, we can incorporate along with samarium, we can incorporate europium and dysprosium.
Okay. Okay, Adira. Thank you.
Okay, ma'am. Can I share my screen? Is it visible, ma'am?
Yes, Srija.
Okay.
Yes.
Okay, good morning. I'm Srija. I'm doing my research work under Dr. Anita Philip, Cochin College, Kochi. So today I'm discussing about my work, the effect of sudden doping on the optical properties on optical and conductivity of thin sulfide thin film formed by chemical bath deposition. So the main objective of my work is to synthesize and characterize a thin film of tin sulfide and sudden doped tin sulfide using CVD method, and to determine which of its property make it a good candidate for the absorber layer of solar cells. So first of all, what is a thin film solar cell? So a thin film solar cell structure is made up of a thin flexible arrangement of different layers. So light absorption and carrier generation occur in the absorber layer. So a solar cell absorber should be efficient in absorbing radiation energy, that is sunlight visible in the visible range. A certain thickness of semiconductor sustainably absorb visible light, and always the absorber layer, we use always P-type semiconductor material, and the window layer is N-type material. So our aim is to prepare an absorber layer material using tin sulfide. So why we use tin sulfide? Means it is abundant in nature, non-toxic, high absorption coefficient, insoluble in water. It has near optimal direct band gap of around 1.3 to 1.5 electron volt, high level of environmental and chemical stability, and it is brown in color, and it shows orthorhombic structure. So we use the methodology or the method of preparation is chemical bath deposition. So why means it is simple implementation, non-sophisticated equipment required, relatively low temperature. We need relatively low temperature for preparing thin sulfide thin film, and we can also have a large area deposition. So these are the synthesis method, and here cationic and anionic solution we use this stannous chloride and thioacetamide as tin and sulfur source. And here we prepare 1 molar solution of tin chloride and also 1 molar solution of thioacetamide. Using some buffer solution and complexing agent, we can prepare the chemical bath. And after preparing the chemical bath, a clean glass slide is dipped onto the solution for 60 degrees. The prepared film was dried in normal temperature. And then we add a zinc dopant like 0.1 gram, 0.2 gram, and 0.3 gram on the tin chloride solution, and the procedure is again repeated. So these are the characterization we done. First of all, the structural characterization. So for understanding the structure, we use XRD analysis. So these are the XRD pattern we got. And here the main orientation is around the plane 1-1. That means the prepared film have orthorhombic structure. And the crystalline size we measured using Debye-Scherrer formula, and the size of the particle is 11.2 nanometer, and these are the lattice parameter we measured. And for analyzing the chemical composition of the prepared film, we consider the EDAX spectrum. So this is the EDAX spectrum of pure SNS. So this is the chemical ratio 50.6 and 49.4. So we got a good chemical ratio of tin sulfide. And this is one of the film, that is 0.2 Zn SNS film EDAX spectrum. And here we can see the presence of Zn in the prepared film. And this is the atomic ratio, that is sulfur in the range of 47.04, Zn 3.51, and Sn 49.45. And this is the same image of the prepared film, and this gives the surface morphology of the film, and we can see a homogeneous surface morphology for the prepared thin film. This is for SNS, pure SNS, and this is 21 Zn SNS, and this is for 0.3 Zn SNS. And this is UV spectroscopy, that is optical characterization. So optical band gap energy of the synthesized particle were calculated for the absorption spectrum. Band gap energy can be obtained from the graph, and we consider the graph of h nu versus alpha h nu the whole square in the region of strong absorption. So extrapolation of the straight line portion of the curve to the zero absorption coefficient value gives the energy band gap. So this is the spectrum, absorbance, wavelength, the characteristics of the prepared thin film like SNS, 0.1 grams Zn SNS, 0.2 grams Zn SNS, and 0.3 grams Zn SNS. And we can see the maximum absorption is taking place in between 500 to 800 nanometer. And using this absorption spectrum, we calculate the absorption coefficient like alpha equal to 2.303 A divided by T, where A is the absorbance. And the value for 0.2 grams Zn SNS, absorption coefficient of the thin film 0.2 Zn SNS is around 10⁴ centimeter inverse. And for SNS, the absorption coefficient is slightly less. And this is the top plot for calculating the band gap energy of thin film. So we got the band gap is ranging from 1.36 electron volt to 1.78 electron volt. So for pure SNS, the band gap is 1.36 electron volt, the direct band gap. And for 0.1 Zn SNS, the band gap is 1.41 electron volt. And for 0.2 Zn SNS, the band gap is 1.44 electron volt. And for 0.3 Zn SNS, the band gap is light high, that is 1.78 electron volt. Okay. So this is the conductivity measurement. We only done the type of conductivity measurement using hot probe method, and the analysis given that for SNS, 0.1 Zn SNS and 0.2 Zn SNS, the film show p-type conductivity, and as the concentration of Zn is increasing, the conductivity is slightly changing from p-type to n-type. So in our case, in the case of solar cell, the main component of thin film solar cell is the absorbable layer. So in thin film solar cell, the absorbing layer is the semiconducting material that absorb the highest number of photons and in response excite electrons into the conduction band. So here we can see in the absorption spectrum, the maximum absorption is taking place in between the visible region, that is 500 to 800 nanometer, and the conductivity also shows p-type conductivity. That means the prepared SNS thin film we prepared using CBD method is very successful, And the 111 crystal plane was the preferred orientation, and the structure is orthorhombic using XRD data. So the precise chemical makeup of the thin film is revealed by the EDAX spectrum, and we got a very good chemical composition. Also, the absorption spectrum is maximum absorption is in between 500 and 800 nanometer. That is, the film can absorb the maximum visible light. Also, the band gap is ranging. We can tune the band gap between 1.36 and 1.78 electron volt. And the material is p-type for low concentration of Zn. And as the concentration of Zn is increasing, the conductivity is slowly changing from P to N. And so these all characteristics match those to the material used as the absorber layer in solar cell. So these are our work. Ma'am.
Okay, thank you, Srija.
Okay, ma'am.
Yeah, that was a good presentation, and I just want to know, have you maintained any particular substrate temperature, or what are the substrates that you have used?
Yeah, I tried from room temperature to maximum 90 degrees Celsius. But as temperature is increasing, here we are using chemical deposition method. So as temperature is increasing, the precipitation rate is increasing. So we always consider around 45 to 60 degrees Celsius.
As the optimum temperature.
Yeah, at the optimum temperature. After 60, the precipitation rate is increasing. That means the film surface is not homogeneous.
Okay, what is the approximate thickness of the film? Have you studied it?
Around 30 micrometer.
And you have a pinhole-free pure film.
What, ma'am?
You are getting pinhole-free film without any.
Yeah.
Kind of.
Yeah.
Okay. And you have said you have prepared. What are the different concentration? What are the different open levels that you have used?
Ma'am.
You have used a zinc, right?
Yeah.
And you said sometimes you say it is 0.1 gram, 0.2 gram, 0.3 gram, and in your graph it is written as 0.1 molar, 0.2 molar.
Yeah, that is in only one graph. It is by mistake. It is
the correct one. Which is
the
the correct one. You are using
gram,
molar
only
ratio?
gram, 0.1, 0.2, 0.3 gram.
Gram in how much? Or what is that weight? Is it in weight percentage, or I just want to know the proportion?
No, in 10 ml of water, 0.1 gram of zinc chloride we added.
Okay. Then just show me your SEM. I suppose both the SEMs are the same, or are they different?
Yeah, for 0.1, 0.2 zinc SNS, we got the same film, but for 0.3, it is like a granular structure.
Okay, and up to 0.2, you have p-type conductivity, and
I can show p-type conductivity.
Okay, so beyond that, you have n-type. Which is preferred, p-type or n-type for the absorber layer?
Absorber layer, it is p-type is preferred, but in solar cell, in my next aim is in solar cell, the window layer is considered as n-type material. So if I can prepare this SNS, pure SNS with the zinc doping, if I can prepare n-type material also, that is good, I think. I don't know.
Okay,
that's
okay. Okay, that's okay. Over to you, Sheena, ma'am.
Okay, Srija.
Hello, ma'am.
It was a good presentation. You have studied the films with the 3 concentrations of the zinc, isn't it?
Yeah.
Which one is the optimal doping concentration for achieving best coefficient, absorption coefficient?
For absorber layer, it is up to 0.2 because in 0.3, I got the absorption peak in the same level, but while measuring the conductivity, it is n-type. I just checked with the hot probe method, and I'm trying to measure the conductivity using hot probe. The work is going on.
Have you checked the thickness of the film?
Yeah, thickness for 0.2 Zeton means in that film we check the thickness that is about around 30 micrometer.
Okay, Srijan. That's fine.
Okay.
Hello? Hello, am I audible? Okay. Is my screen is visible? Now it's visible now. Then can you share my PPT? Okay. Okay. Hello? Okay. Okay, good morning to all. My name is Dr. Jean Maria Matthews. I'm working as Assistant Professor at Department of Physics, Newman College, Todupuzha. The title of my presentation is Wear and Friction Properties of Peak Ceramic Nanocomposite Reinforced with Sol Gel Derived Nano-Layered Fillers. There are plenty of opportunities in different strategic field for oilless ultra-low friction lubricant that can control the noise as well as enhance the performance and life of the structural components. Development of such solid lubricant has been strongly taken up in metal matrix composites and alloys for more than decades rather than ceramics. The reason is that ceramics are brittle and not machinable. Moreover, the high density and high temperature processing are also limiting the development of solid lubricants based on ceramics. Actually, the lubricant is a substance that is introduced to reduce the friction between moving surface. Usually, we are using liquid lubricants. Liquid lubricants allows dramatically decrease the coefficient of friction. Today, in our daily life, we are dealing with various machines. Frictional loss is one of the important laws in machines. So while we are using liquid lubricants, it is impossible in certain applications in which ceramic parts operates under the condition of high temperature, vacuum, or corrosive environment. In such situation, continuous supply of solid lubricants to the ceramic surface may be provided by the ceramic material itself if it is a composite material with a ceramic matrix containing dispersed particle of the lubricant. But the low machinability of the ceramics prohibit such applications. So certain composite self-lubricating materials are designed. This slide shows some innovative lubricant composite, which is fabricated by incorporating certain ceramics in polymer matrix. Such hybrid composite designed out of suitable ceramic dispersion in polymer matrix can improve the wear resistance without affecting the toughness and machinability of the polymer. So here, this work introduced ceramic polymer composite self-lubricating material. The processing of nano-layered ceramic filler through sol gel technique to impart lubrication effect in ceramic polymer hybrid nanocomposite having thermal stability, low friction and wear properties is discussed in this work. Here I have selected a polymer called PEEK, polyaryl ether ketone, as polymer matrix. Here this polymer possesses high temperature stability, low moisture absorption, density of 1.3 gram per cc, and almost high melting point of 370 degrees Celsius, and glass transition temperature 70 degrees Celsius, and high machinability. But its disadvantages are its hardness is very low, it poses high wear, and it shows swelling at high temperature. So in order to control or enhance these disadvantages, I have incorporated certain ceramic fillers into it. This is the characterization of pure PEEK polymer. And the particle size and some images are shown here. And for enhancing its disadvantages, I have incorporated alumina and lanthanum phosphate grains, which are synthesized through sol gel route, and the sol gel route for the synthesis of bomite sol and the lanthanum phosphate sol is shown here. These salts are dried, and I obtained alumina and lanthanum phosphate grain, which are incorporated into PEEK matrix. This is the same microstructure of alumina and lanthanum phosphate grains. This is the experimental part for the fabricating lanthanum phosphate alumina PEEK nanocomposites. This alumina and lanthanum phosphate grains separately dispersed in PEEK polymer matrix, and it's blended properly. After hot melting, ceramic polymer hybrid nanocomposites are obtained. This is subjected to thermal expansion, wear and friction properties. This is the same microstructure of PEEK alumina nanocomposites. This images are for different percentage of loading of alumina grains in polymer matrix. This shows for 10% loading and 20% loading, it shows proper blending between alumina grains and polymer matrix. After that, it shows some detachment of ceramic fillers from the polymer matrix due to overloading. The same for lanthanum phosphate grain in PEEK polymer. This is the variation of thermal expansion of PEEK alumina lanthanum phosphate nanocomposites. The expansion of PEEK polymer is controlled due to the incorporation of ceramic fillers. The hardness of the PEEK alumina lanthanum phosphate hybrid nanocomposites shown here. The hardness measurement is done using Climax Vickers hardness tester. The polished sample is subjected to a weight of 100 gram for time duration 15 minutes. Then it's observed that with the increase in the grain loading, the hardness of the composite is increased. And this is the variation of wear properties of polymer ceramic composites. It's observed that with the incorporation of lanthanum phosphates grains and alumina grains, the wear properties is reduced up to 30 volume percentage. Beyond that, the wear is increased due to the detachment of ceramic particle from the polymer matrix. This wear testing is done in a polishing machine. The sample is polished for 1 minute, and initial and final weights are measured. The weight loss is measured for each percentage of ceramic particle loading, and it's observed that up to 30%, the wear resistance of the polymer ceramic composite is enhanced due to the incorporation of these grains. In conclusion, the study brought out a range of wear resistant and thermomechanically stable polymer ceramic hybrid composite that can find applications for fabricating bearings, sleeves, and interface thin films. The appropriate loading limit of ceramic face was optimized as 30 volume percentage. The incorporation of alumina lanthanum phosphate to peak enhances the wear resistance and hardness of the composite compared to pure polymer. Thank you.
Thank you, Jean Maria. And I have few doubts. Like you were talking about the maximum loading, like it's around 30% or something, right?
Yes,
You are talking about the maximum
yes,
loading.
ma'am. Yes,
that
ma'am.
Yeah, and is it because of something like the percolation threshold or something like that?
Yeah, yeah. After that, the detachment of particles is observed, the grains, or due to the overloading. Up to 30%, we are getting low wear loss and hardness also.
So you are preparing the polymer and the composite.
Not polymer. I have
You are taking the polymer
grains.
and you are preparing the grains and loading the polymer with the grains, right?
Yes.
And you have a hybrid nanocomposite formed.
Yes, ma'am.
And you are making it in the form of sheets or what are you doing?
Actually, I made it in the form of pellets. For testing the wear test and hardness, we need pellets. So I fabricated in the form of pellets.
Okay. So when it comes to a device or comes to application level, what could be the form? What is the advantage of?
Actually, this is for machine parts.
Okay.
So we can design this peak polymer is highly machinable. We can by incorporating 30% of filler particle, we can retain its machinability. In any form, we can shape it.
You can modify the hardness. You can modify.
Yeah, wear resistance also.
Wear resistance. Okay. What about the stability?
Thermal stability.
Yeah.
Actually, it's a polymer, no? So up to 500 degrees Celsius, we can. It's stable. This composite is stable.
You have tried the curing of peak.
Yeah. Yeah.
Okay. Thank you, Sheena ma'am.
Okay, Jean, that was a good presentation. So what is the role of this nano-layered fillers in improving this wear and friction?
Actually, this lanthanum phosphate possesses layered structure. This layered structure render self-lubricating property to the polymer composites. Actually, for lubrication effect, we are using liquid lubricants like oils.
Okay.
These have some disadvantages. We can't use such lubricants in high temperature application or vacuum application, etc. But by incorporating these fillers, these ceramic fillers into the machine parts, that will act as a self-lubricating material. Then there is no need of liquid lubricants like oil and all.
Okay. Okay, Jean. That's all.
Thank you.
Okay, thank you. Can we leave now?
Thank you.
Okay, thank you, Malini.
Thank you, ma'am. Thank you, ma'am.
Okay, bye-bye.
Record. ഇതാണോ? ആയിരിക്കും.
Recording in progress.
Hello. Yes, yes. Hello, ma'am. Can I share the screen? It's disabled. Ma'am, please allow me to share my screen. Hello, am I audible? Hello. Okay. Is it visible? Hello?
Yes,
Can I start the presentation?
okay, you can start.
Good afternoon all. Today my topic of discussion is development of nanocomposite with the LDP and graphene nanoparticles by means of melt extrusion method. The matrix material which we use for the study is low density polyethylene. As you all know, HDP and LDP are the most common polyethylene materials which are used widely. I selected this material because it's a soft, flexible and lightweight plastic material, and also it have good corrosion resistance. And the filler material which we used is graphene nanoparticles. It is locally purchased, and these two, the filler and the composite material is mixed with the melt extrusion method. We pelletized a sample at 448 Kelvin. And the samples were prepared using ASTM standards. By varying the amount of graphene nanoparticles from 2 weight percentage to 10 weight percentage, we had prepared 5 samples, and we compare it with the pure LDP sample also. The characterization techniques which we are used is UV visible spectroscopy and differential scanning calorimetry. First, we will discuss about the UV visible spectroscopy. From figure itself, you can see that this is a virgin one, black one. Virgin material does not have any absorption, and it is seen that as the amount of filler material is increased, the absorption is found to be increasing. This is due to the great surface area, larger delocalized pi electrons, etc. And it is also seen that the 230 nanometer characterization peak is also seen here. That peak is due to the pi star plasma value. Now we are going to the differential scanning calorimetry study. And in this case, we have used the 5 samples and the virgin material. You can see that this is the glass transition temperature happens here, and the peak value of virgin LDP is shown at 324.7. We can round it as 325 Kelvin. And due to the this glass transition happens due to the partially ordered interface between the lamellae and the amorphous region, and it is also known as glass transition or alpha transition of LDP. And here, with the increase of graphene, that is a filler material, it is found that LDP matrix shows variation, glass transition temperature variation towards a high value. That is here, it is noted as 327.5 Kelvin.
Good morning. I'm
And this
Shrija.
indicates
I'm
the
doing my
effect of
research work.
nanoparticles in the mobility of the molecules in the matrix. These graphene particles have some effect in the mobility of particles. Now we are going to the melting behavior. This peak shows the melting behavior. And in this thermogram is used to determine a number of parameters here, that is one set of temperature, peak temperature and heat of fusion. So melting temperature of crystalline polymers normally depends on the size and perfection of their crystal units. Here the melting temperature of LDP depends on the filler particles of the composite. The virgin LDP shows the melting temperature at 389.42. You can see it here. The peak melting temperature of LDP composite is shown to be slightly increasing with the increase of the filler. This is probably due to the fact that graphene nanoparticles absorb more heat during the melting of composites. The melting endotherm also starts at lower temperature in these composites than the virgin LDP. This is due to the larger crystalline size and narrower size distribution of LDP in the composite. So these features indicates the improved thermal stability of the composite. And it is also observed that the delta H fusion value, it is also found to be increased with the amount of filler particle. Now we are coming to the crystallization behavior of the material. The DSE thermogram of virgin LDP and its composites in the region of crystallization is recorded during the cooling scan. The crystallization behavior is over from the temperature range 398 Kelvin to 363 Kelvin. The increasing concentration of graphene nanoparticle in the LDP matrix resulted in the decrease of TCO, that is the onset temperature of crystallization is found to be decreasing. The decreasing TCO clearly indicates the delay in nucleation. Nucleation means the ability to crystallize from the liquid phase. In the onset temperature usually indicates the beginning of crystallization process. And the maximum of exothermic peak indicate the occurrence of spherulite impingement. The increase of peak crystallization temperature of the LDP with the increasing concentration of graphene powder suggested that the crystal growth of LDPE in the composite would take place at higher temperature, leading to larger crystalline size and improved crystal perfection and narrower crystal size distribution. And in this graph, you can also see that as the amount of graphene percentage is increasing, the crystallinity of the material is found to be increasing. To conclude, a series of LDP graphene nanoparticle composites have been prepared and extensively studied for the optical and thermal behavior. The LDP with graphene composite exhibited higher thermal stability than neat polymer. And this work clearly shows graphene powder can be effectively used as reinforcing material in thermoplastic LDP matrices. It's a good alternative, commonly used LDP composites with the inorganic and organic fillers. Since nanocomposites are scoped for the future and considered as a material for next generation, there is an imminent requirement to investigate the durability of this nanocomposite in different environmental conditions and to extend its applicability in various versatile fields. Thank you.
Audience can ask questions.
Pardon, sir? Not audible.
Audience, you can ask questions.
Okay.
Any questions from the audience side? Okay, can I ask one question?
Yes, sir.
Okay. What is the final outcome of your work?
Pardon, sir, what is the
Final outcome.
Final outcome? Okay. Okay, okay.
Where you can apply this material? What is the potential use of your material?
This material can be, while adding graphene, we can improve the conductivity of the material so that we can use this material in different applications, electromagnetic shielding like that, and in biomedical materials, in sensors, etc. A membrane type of this material can be used in a variety of applications.
But you have not done any application work, right?
No, sir.
Okay, then what about your extrusion method? You didn't mention anything about that method.
Pardon, sir?
Melt extrusion method.
Melt extrusion method.
Yeah.
Melt extrusion method means we are heating the material up to its melting temperature so that we can mix the matrix and the filler without any solvent.
Okay. Okay, but didn't include any slide on the
Okay. So.
timing, sir?
I do have some doubt about differential scanning colorimetric graph, which you have shown. So you have observed that when you are when there is an increment in graphene percentage, you said something like delaying nucleation occurs.
Yes. Yes, sir.
Why is it so?
Because this graphene nanoparticles absorb a lot of heat.
And how is it connected with the crystallization behavior?
Crystallization behavior we are studying in the cooling phase.
Could you please show me that slide once again? Actually, I missed. Okay, okay, crystallization behavior increases. Okay. Could you please also show the DSC graph just before this? Okay, 360. Okay, your crystallinity also is increasing. Both are showing the same trend, right?
Yes, sir.
Okay, what is your? Yeah, your final conclusion is not quite understood by me. So in connection with the same question of Dr. Thomas.
Okay, by this study, what I mean is with the addition of this graphene particle, the thermal stability of the material is found to be increased and the quality of crystal is found to be increased.
Okay, thank you.
Okay, sir, thank you.
Any more questions? Okay, thank you.
Okay.
Good morning, ma'am. Good morning, all professors and judges. Can I start?
Yeah, you can start.
Thank you, sir. My slides are viewable?
Okay, it's okay.
Yes.
Oh, okay, sir. Thank you. 1 minute. Okay, today I'm talking about a fully sustainable approach for the preparation of immaculate nanotubes. And it's applied as, it's just showing as an electrosensor for paranitrophenol using by loading silver on immaculate nanotubes. In this discussion, we going through these parts: introduction, experimental section, result and discussion, and conclusion and references, question and answers. So introduction, what are immoglates? Immoglates are actually naturally occurring aluminosilicate based single walled nanotubular clay minerals. It's obtained or found in soil nearer to volcano. So it's found in volcanic ash because it needs more alumina and silica content. It's actually formed by the combination of alumina and silica. So its general stoichiometry, we can simply say that outer surface is made by alumina particle and inner tubular wall is made by silica. And
excuse me,
yes,
are you moving ahead with the slides?
yes,
Okay, now only the corresponding slide.
yes, sir. I think some problems, so I will show like this.
Yeah.
And in this thing, one more thing, it have more advantages. It's inner and outer surface containing OH groups, so it can carry many kind of materials, metals, and many kind of biological molecule also. So it is used as DNA carrier also. So it is a material which very much potential applications. So in this work, generally in past works, mainly they extracted or taken from these volcanic ashes. But here we try to prepare in our lab conditions. In lab condition, most of them are prepared from TEOS as silica source, but here we used as RHA, rice husk hash as silica source. After the burning of rice husk hash at higher temperature, we dissolve that rice husk hash into 3 molar sodium hydroxide, and we convert it to sodium silicate, and here sodium silicate is the silica source, and we applied fatty acid, a naturally occurring fatty acid, lauric acid, as template, how it's act or how it's help to form immoglate nanotubes within few days. Actually, it's a time taken process, 3 to 10 days. Here we only treated 4 days. So the other thing is we load silver nanoparticle on this immoglate nanotubes for it makes conducting. Actually, it's an insulator material, and we used it as a nitrophenol sensor. So when we go to experimental section, we just taken everything in millimolar concentration. So into lauric acid solution, we add aluminum nitride in millimolar concentration. After treating it in 80 degrees Celsius, we add sodium silicate. So after adding the sodium silicate, we slowly set its pH to circumneutral pH, that means 7, using low molar sodium silicate. After that, at 90 degrees Celsius, we treat it in hydrothermal treatment. That means we treat it in autoclave for 4 days. After that, we purifying this material. We load it by adding we load silver to immoglate using AgNO3 as a silver source, and by the use of ascorbic acid as reducing agent. And this material we coated on carbon paste electrode, and then we used it for electrosensing studies using for nitrophenol. And we can go to the resultant discussion. In this characterization techniques, we used first as FTIR. In FTIR, we just proven that it's a hybrid material. It's a combination of lauric acid and immoglate nanotubes. In the preparation of blank sample, we don't use lauric acid, so it forms an actually combination of allophane and gibbsite. That means it's only containing aluminate and silica. There is no formation of immoglate nanotubes, so the peaks also have very poor, and there is no organic peaks. There is no lauric acid peaks because it's not containing lauric acid. But in the case of other two samples, this is lauric acid containing immoglate nanotubes. So here we can observe the lauric acid peaks, as well as we can observe two major peaks obtained in imogolite. This is SiO-Si peaks and SiO-Al peaks. So we can say that the hybrid material is formed at the same time. We can obtain some imogolite peaks. And after that, we do TGA. According to TGA results, we can say that when the material heat at inert condition, the lauric acid decomposes from 300 to 400, and its weight losses up to 50 percentage. And the interesting thing is, when we compare with the 3 weight percentage AgIMO NTs and LaIMO NTs, the weight loss is 3 percentage. The final weight percentage weight loss is 3 percentage. So we can tell that 3 percentage Ag loading is successful. And finally, we are going to XRD. According to XRD results, in blank IMO NTs without lauric acid functionalization, it forms gibbsite or bombate. Gibbsite also a variant of bombate. So it forms gibbsite and bombate. And we can observe some unreactant silica also in all the samples. That's the reason for this amorphous peak, starts from 20 to ends into 30. And but in the case of lauric acid loaded samples, we get many peaks of imogolite. This is the 110 plane of imogolite, and 001 and 211 peaks of imogolite. And we can observe a peak at 3. That's the 100 plane of imogolite. It's here. Actually, when we draw with more resolution, we can observe that peak. This is a major peak of imogolite, and it passing through the center of the imogolite nanotubes. So it's 100 plane. This is the explanation of imogolite XRD peaks of imogolite nanotubes. And in the interesting thing is, we can observe the silver phase outing at 5 weight percentage AgLi IMO NTs. That is also underlined by the TEM images. Here we can see that in the case of blank IMO NTs, there are some circular shaped formation of aluminate and silicon nanoparticle. But in the case of lauric acid functionalized imogolite, we can saw the formation of some tubes on lauric acid bed. Actually, lauric acid formed as a layer, and on that layer we can observe some tubes. In the case of silver loading, 5-8% silver loading, we can observe some silver particle nanodots at 8 nm. And it also show in SCED pattern also. And finally, we are going to the electrosensing part. In electrosensing part, we can say that LAIMO NTs actually it's performing as an insulator, but by Ag nanoparticle loading, it becomes conductive. So we can say that our work is successful, and we can just show that electrosensing is possible by loading a few amount of silver on imogolite nanotubes. And this is the electrochemical cyclic voltammetric profiles. According to these profiles, we can show a reduction peak of 0.8 volt, minus 0.8 volt. It's a characteristic peak of reduction of nitrophenolate ion from nitrophenolate ion to para-hydroxyl aminophenol. And this para-nitroso aminophenol again oxidized to para-nitrophenol That peak is here. It's not clear actually because the graphs are small. That's why happening here. And at this reduction and oxidation, here silver also happens some oxidations. In the case of silver, it cases two kind of oxidation. Firstly, it oxidates to Ag plus at 0.3 volt, and it again oxidates to Ag2 plus. It's happened here. We can observe some two twin peaks. Silver loading is very less in these samples, so that's why I thought the peak is very small. It's Ag plus formation, then Ag2 plus formation also happen here. This oxidation also reduces nitrophenol, and that leads to the reduction of nitrophenolate ion, and electrosensing is possible by loading silver on immobile nanotubes. That's I observed. And finally, we are going to conclude. According to our results, we convert a waste biomass, that means rice husk, to sodium silicate as a good reactant. And here we can say that lauric acid templation is also a good thing. So functionalization through lauric acid leads to the formation of immobile entities within few days. And the silver loading also make it as a conductor from insulator. And millimolar sensing of nitrophenol is also achieved. So the work is success, and this is our conclusion. And these are my references, and we can go to question and answers. Thank you. Thank you.
Ryan, sir, have you any questions?
Yes, you are talking about the applications of these IMO nanotubes as DNA carriers. How is it?
Yes, sir.
Is there any references regarding that, or how is
Yes,
it?
sir. Sure, sir. Sir, it have a paper, it's published on RSC. They say that immobile nanotubes have some interaction with a phosphate group of DNA. So they, in that work, they used it as messenger RNA. If you are interested, I will forward, sir, definitely.
What is it? Is the
Sir?
outside the surface?
Sir, it's not audible actually. Can you ask again? Hello?
Can you hear me now?
Yeah, now I am audible, sir.
Okay. So DNA is polyanionic, and how much is the charge density as per your understanding about the charge density of these nanotubes?
Immobilite. In that paper, actually, they are not talking about charge density. They are mainly talking about the surface area and the presence of aluminol groups. That means OH groups on the surface of the immobilite outer surface. They telling that these OH groups interact with the phosphate groups present on the DNA, and they can carry DNA. They can these immobile nanotubes can carry DNA.
Now, what is your next direction in which you will be proceeding? What's the future?
Sir, in this belong with this work, I do the photochemical reactions also. So it's also successful, and it is actually it's more good for photochemical reactions. That means photo reduction, catalytic reduction. So so I completed that works also. So I am waiting for the publications.
Okay.
Actually, now I am not working on that field.
Okay, thank you.
Okay.
Can you show the 10 images?
Sure, sir, sure. Is it visible, sir?
Okay. have you measured any dimension?
Yes, sir. Actually, it's showing 1 to 2 nm diameter. Actually, it's just the formation. Actually, it's a basic, it's a small formation of immaculate nanotubes we can observe. We cannot tell that it's successfully it forms a tubes because we only treated as 4 days. Actually, it's a time-taking procedure. Actually, these tubes are formed within very. It's a time-taking process. It takes
Okay.
more days.
Because by seeing this figure, we cannot say it is tube-like structure. Then did you measure the aspect ratio?
No, sir, no, because actually
Okay,
TEM
it's
images
okay,
is
it's
not
okay, no
clear. I
problem.
think
Then
it's an
what is the confirmation about the SID pattern?
according to SAD pattern, it's a semi-crystalline or it's a in-between stage of amorphous and crystalline nature. So according to this, we can say that it's a in-between stage, and we can observe some silver plane also.
Is it clear? 111 plane?
Yeah, its AGS 1-1 plane is observable here.
Oh. Okay, thank you. Any
Thank
more
you,
questions from audience side?
Yes, sir. Thank you. Thank you.
Hello, ma'am. Is it audible?
Yeah, it's audible.
Yes.
Okay, you can start.
Is my slide visible? Okay. Sorry, ma'am. I am looking it. Is it visible, ma'am? Okay. So, good afternoon all. So today I'm going to present the topic enhanced energy storage and pyroelectric properties of PVDF, TRFE, CTFE based on nanocomposite films. Coming to the background behind this work, we know that the demand of energy to power various devices and electronic power systems is rising globally. So to address this energy demand, the challenge is to adopt various approaches to harvest energy. And we know that there are so many materials that respond to different kinds of environmental stimuli like mechanical vibrations, heat, electric field, magnetic field, and in response to that stimuli, they will produce a new electrical output. And these electrical output can be stored or harvested for various applications. And basically the temperature and electric field dependent properties and also the dielectric properties of the materials make them a potential candidate for various energy related applications. And we know that there are a category of materials known as ferroelectric materials. They possess such multifunctional properties and can be devised for various energy harvesting applications. And also we can use ferroelectric polymer ceramic composite technology in which the merits and demerits of each such phase can be tailored and we can tune for designing new systems. And coming to the materials and methods I adopted, I selected the sodium niobate ferroelectric as the filler part due to its high electric permittivity and also low cost, non-toxicity. And mainly it is electric field, it have electric field dependent polarization. And coming to the polymer part, terpolymer, PVDF, TRFE, CTFE is selected as the matrix due to its inherent relaxer behavior. And also they possess the temperature dependent and electric field dependent polarization that can be used for harvesting energy. And the sodium niobate nanoparticles is synthesized using sol-gel method, and the composite films are prepared by solvent casting method. And here the pure polymer is abbreviated as PVTC, and with the different loadings of sodium niobate, it is abbreviated as PVTC 5 nm, PVTC 10 nm, and PVTC 20 nm. And coming to the synthesis method, sodium niobate nanoparticles are prepared by sol-gel process. Here the stoichiometric coefficients of sodium carbonate and ammonium niobate is selected. And citric acid is used to enhance, and ethylene glycol is used to used as a stabilizing agent. And finally, the final solution is stirred, dried, and calcinated at 700 degrees Celsius to obtain the pure phase. And terpolymer nanocomposite films are prepared by solvent casting method. And for that, the polymer part is fixed and the sodium niobate part is varied. And after complete dissolutions, films are casted in a petri dish, and it is dried at 60 degrees Celsius. And to improve crystallinity, it is again heated at 100 degrees Celsius for 2 hours. And coming to the results, the XRD results obtained for sodium niobate nanoparticles obtains confirmed is purity, and it was also confirmed by comparing with the JCPDS data. And average crystalline size found to be 28 nanometer. And coming to the XRD data of composite films, we can see that the presence of electroactive phase of the polymer in each composite films, and also the peaks corresponding to the sodium niobate also get enhanced with the loading. And coming to the FTR studies, the FTR studies depicts that the electroactive polar peaks of the composite films that improved. And coming to the morphologic studies, we can see that the majority of the nanoparticle synthesis as spherical, and also the despacing corresponding to the planes 101 and 141 were also marked using HR-term micrograph, and elemental composition were confirmed using EDA spectrum of the sodium niobate nanoparticles. And coming to the morphology of the nanocomposite films prepared, we can see that the morphology of the pure films changed with the filler addition. That is one of the main characterization of solvent casted film. And the electrical study is mainly done using dielectric properties, and dielectric properties of the composite films improved with the filler addition. That is actually one of the main characterization of solvent casting process, and it is mainly due to the interfacial charge polarization between the filler and the polymer part. And coming to our main storage related studies, actually the energy storage related studies were done using ferroelectric P hysteresis loop studies. And from the loop, it is clear that actually the green portion of the graph, which is actually used for recovering energy density, and the pink portion is actually the loss energy density. And for exactly calculating the energy discharge energy density, we have to integrate EDP from the limit P remanence to P maximum. And this is the result that is obtained for the pure polymer, and with 10 loadings of sodium niobate and 20 loadings of sodium niobate. And also the energy in another approach, also the energy harvesting studies were done. That is, it is a thermodynamic approach. Here also ferroelectric P hysteresis loops were used to study the pyroelectric energy harvesting property. And here, 2 hysteresis loops are obtained for 2 different temperatures. And here a loop is obtained, and here the area enclosure the loop is used for calculating the energy harvesting density. And this is the pattern that is obtained for the composite film. So we can see that here also the polarization of the nanocomposite films is changed for different temperature, and this change in polarization is used for calculating the energy harvesting density using pyroelectric method. And this is actually the comparison of the result that is obtained. The discharge energy storage density improved with the filler addition, and also the pyroelectric energy harvesting density also improved with the filler addition. And coming to the conclusion, various polymer nanocomposite films were prepared, and various structural, morphological, ferroelectric, and energy storage energy storage using two different approaches were carried out. And nanofiller incorporation actually improved the storage properties. And we can tune different polymer and filler part to develop such storage devices for various applications. And this is the references I used. And thank you.
Thank you.
What do you mean by this pyro harvesting property of this?
Okay, sir. Actually, by pyroelectric harvesting, actually we meant to harvest the energy using the low grade heat. From heat, we are harvesting the energy density from that.
Can you say what is the novelty of your work compared to literature work?
Sir, okay. Here actually the polymer that I selected is PVDF, TRFE, CTFE, and it is actually a little bit having a relaxer behavior, and that is doesn't used much in energy harvesting aspect using pyro technology. So that is mainly we used for this polymer having certain novelty for this type of study.
Then what about the comparison output of your work with others' work comparison?
Comparison. Okay, sir. Actually, here here we did this work at a very low heat and at very low electric field. So due to that, even though our the numerical value that we got is a little bit average compared to others, that can be maybe at future we are planning to improve much further.
Okay. Then what was the particle size of the composite?
Composite or sir, is it the sodium niobate nanoparticle? Yeah. Okay. That actually the crystalline size was found to be 28 nanometer. That we calculated using Scher equation.
28. Okay. Polymer with the filler.
Yes, sir. It was actually calculated for the nanofiller itself for.
Okay. Okay, thank you.
Okay, thank you, sir.
Questions from audience? Okay, let us have next.
Okay.
Hello, is it audible?
Yeah.
Is my screen visible?
No.
Okay. Can you see? Good afternoon, everyone. I am here with my topic, effect of curing agents on chloride-induced corrosion. First of all, introduction. As we all know, corrosion is referred to as the process of deterioration and consequent loss of solid metallic material through chemical or electrochemical attack by its environment. And it requires an anode, cathode, electrolyte, and an electrical connection between the anode and cathode for the transfer of electrons. And the concrete pore water acts as the electrolyte, and the body of the reinforcement provides an electrical connection between the anode and cathode. And this figure shows the reaction that takes place at the anode and cathode. First, at the anode, Fe forms Fe2 plus 2 electrons, and this Fe2 plus pass into the solution, and these 3 electrons moves into the cathode, and where these 3 electrons react combines with the oxygen and water from hydroxyl ions. These hydroxyl ions then combines with the ferrous ions to form ferrous hydroxide, which is then converted by further oxidation to rust. The main objective of the study is to find the effect of curing compounds and integral waterproofing compounds and corrosion properties of
Can you show the respective slides?
Yes, sir.
We can see the introduction slide only now. The title slide only is visible now. Yes, now it's slide number 6.
Okay.
Yes, it's moving now.
Okay.
Okay. Next is methodology. These are the methods that I follow. First one is the literature review, then the characterization of material, then the mixed design of mortar, the 1:3, and the durability and corrosion monitoring techniques, and final the analysis of result. These are the materials that are mainly used in the study, that is cement, fine aggregate, external curing compounds, superplasticer, cornplast, WL, and crystalline waterproofing admixture. External curing compounds are applied to the concrete surface to retain the moisture and promote the proper hydration during the curing process. And this is applied as a thin film on the concrete surface to slow down the evaporation of moisture from the concrete, as shown in the figure. And in this study, mainly 2 types of external curing compounds are used, that is water-based and acrylic emulsion-based. And the next one used is integral waterproofing admixture, and it is makes it, and this addition of integral waterproofing admixture makes the concrete more resistant to water penetration, and these are added directly to the concrete mix, and this works by filling the capillary pores and micro cracks in the concrete. And mainly 2 types are used in the study, that is crystalline and cornplast WL. These are the mix design. In this mainly these are the mixes that I have prepared. First one is M0 is the control mix. Then CN100 is cornplast. CN100, CN200, CN200 are different percentages of cornplast, and CWP is the crystalline waterproofing admixture that are used in 3 percentages. These are the durability tests that are conducted. First one is water permeability. This is conducted to determine the rate of water flow through the material. Then water sorptivity. This is to determine the measurement of water absorption rate, and water absorption is done to find out the water absorption values of different mixes. And the last one is RCPT. This is the permeability of the specimen to chloride ion can be evaluated. Corrosion test. This is half cell potential is the corrosion test that I am conducting. That is, it helps, it measures the electrical potential difference between the surface of the concrete and the reference electrode, and it helps to find out the probability of corrosion tendency, and is used to detect the areas of specimen at the risk of corrosion. And a lollipop specimen is casted to test the corrosion. This is how the specimen is prepared. First one, a long steel bar is cut, then heat shrink tube is applied at the end of the steel bar, then it is placed in the plastic mold, and then the mortar is placed. Then after 24 hours, then it is epoxy is applied at the top and bottom of the specimen. Then after drying, the specimen is ready for the curing and testing. These are the results of compression, compression test. First, From that, these inferences are being obtained. The 7-day strength of the 7-day strength is higher for the specimen with external curing compound than the control specimen, but the 28-day strength is more for water cured control specimen than external curing compound because of the inhibition of the cement hydration reaction within the concrete, and the rate of gain of compressive strength reduces substantially for external curing compound due to the unavailability of sufficient water in the pores to maintain the rate of reaction. And also, and for internal curing, integral curing compound, the 7-day and 28-day strength is more than controlled specimen, and this is because of the improved microstructure and reduced porosity. And among integral curing compounds, CN200 and CWP 2% are the optimum percentage and has the highest compressive strength. And comparing the external and integral curing compounds, ICC has higher value of higher compressive strength than ECC and control specimen. These are the result of water absorption. From this, control specimen shows lower value than the specimen with the external curing compound because the water cured, well cured specimen allows more hydration of cementitious material, and A shows lower value than water-based curing compound because A forms a thicker and more impermeable film on the surface of the mortar. These are the result of sorbtivity. Curing compounds show higher rate of water absorption than the control specimen. The higher value of the water sorbtivity indicates deeper penetration of water into the mortar and thus an inferior performance. This is because of the fact that the value of sorbtivity decreases with the increasing porosity. And the last one is half cell potential. The result of half cell potential. The graph shows the initial values of the wet and dry cycle that I have done. This is an ongoing project, so the final values are yet to get. So the initial readings are within the range with below minus 200. That is that means that the corrosion is absent. Coming to the conclusion, from the obtained result that integral curing compound has a higher compressive strength than the control and external curing compound. The control specimen has lower water absorption than external curing compound, make it more durable and reduce permeability. And control specimen have lower water absorption than the integral curing compounds. And the values obtained after initial wet and dry cycle shows that the specimens are in the specimen the corrosions are absent. These are the references. Thank you.
Prime Minister, any question?
Could you please show the introduction slides again? I missed it.
Okay.
Actually, it was not moving at that time. Okay, the third. Yeah, this slide. Okay, what is the main finding of your study?
Actually, this is an ongoing project, so I have I didn't get a final conclusion. So this is ongoing. So what I got, I presented. So some ongoing project.
Okay, thank you.
Work is going on. Okay.
Yes.
Okay, thank you.
Okay, thank you.
Let us go for the next.
Hi, madam. Am I audible?
Yes.
Is the slide visible?
Yes, it is audible and visible.
Okay, thank you, sir. Let me start.
It is audible and visible.
Okay, sir. Okay. Good afternoon, one and all. I'm Ria Sebastian. I'm a guest lecturer in the Department of Physics, Newman College, Thodupuzha. Today I'm going to present the topic, the thermal nonlinearity study in anatase, bruchite, and rutile phases of TiO2. First, move to a small introduction. As we all know, the nonlinear property of any material can be tuned by tuning the various properties like crystallographic phase, morphology, linear absorption, particle size, etc. A nanoparticle is a particle having size in between 1 and 100 nanometer. And when we reduce the size of a particle to this nanometer range, we can tune several properties of the materials, especially the nonlinear properties. Move to the instrumentation. In the present work, the scan study is used for do the nonlinear characterization of the material. For that, a blue diode laser was used. The laser beam is allowed to fall on the sample, and the sample scan from -z through the focus to the +z distance. And the beam coming out of the sample is split by using a beam splitter into two. And in the present study, only the closed aperture laser scan characterization is carried out. And for that, before falling to the detector, the sample is allowed, the rays from the sample is allowed to pass through an aperture. The different constant components and their specifications are listed inside the table. The experimental setup that we have in our lab is shown here, and the beam characteristics are 405 nanometer diode laser, blue laser is used for this purpose with a beam spot size 14 micrometer, and power of the beam used is 80 milliwatt. To do the standardization of the sample, I took the curcumin dye for this purpose. For that, I mixed 1 ml curcumin powder in 5 ml, sorry, 1 mg curcumin powder in 5 ml water. And then the characterization is carried out by using this diode laser. And I got a transmittance versus Z plot of the closed aperture research scan like this. There is a peak which is followed by a value which is a clear indication of the negative nonlinear refractive index of the material. And I got a value of N2 in the order of 10 raised to -11 meter square per watt, which is in good agreement with the literature values. Move to the result and discussion. Here I took the TiO2 for the study. TiO2 has eminent features, good features and applications in variety of fields, including photovoltaics, photocatalytic, nonlinear optical devices, etc. It possesses three different crystal phases, anatase, bruchite, and rutile. Usually it shows an amorphous nature at the room temperature. And when we anneal the sample, we got the anatase, bruchite, and rutile phases. And annealing above 600 degrees Celsius at high temperature, that will give the pure and stable rutile phase of TiO2. In order to prepare the TiO2 nanoparticle, a sol gel method was used with TTIP as the precursor, and different concentrations of oxalic acid is also incorporated into the precursor to prepare the TiO2 sample. To prepare the nanofluid for the scan study, I mix 1 mg of nanoparticle in 10 ml water when it is ultrasonicated for 30 minutes. So the different samples that I have in this study, 12 different samples in 4 different categories, 4 different temperatures. One is as prepared temperature or room temperature, and then the samples with 400, 600, and 800 degree annealing temperatures. And in each annealing temperature, there are 3 different samples without oxalic acid, with 25 and 50 ml oxalic acid samples. The morphological characterization is carried out by using the FESM analysis, and the morphology is an agglomerated spherical-like morphology for all the samples. And the different average particle sizes of the different samples are listed inside the table, and it can be seen from the table that as the annealing temperature increases, the average particle size increases, and at a particular annealing temperature, with the amount of oxalic acid enhancement can be observed in the particle size also. Then X-ray diffraction characterizations were carried out, and the XRD pattern of the sample at a room temperature is here, S1, S2, S3 samples. Clear, sharp crystalline peaks are not visible, so I considered it as amorphous. And when it is annealed to 400 degrees Celsius, 3 different samples are here with 25, 50, and 0 ml oxalic acid. And as the amount of oxalic acid increases, the rutile phase of TiO2 begins to emerge. In the case of 600 degrees Celsius samples, for the first sample, S7 sample, there is a peak corresponding to anatase. But from there onwards, from S8 onwards, only the rutile phase of TiO2 is visible there. In the case of 800 degrees Celsius sample, irrespective of the amount of oxalic acid, all peaks are corresponding to the rutile phase of TiO2. Then average crystallite size is calculated from the Sher equation, and it is listed inside the table. And as the annealing temperature increases, an enhancement can be observed in crystallite size. Then in order to find out the different phases, the percentages of anatase, Brookate and rutile phase of TaO2 in each sample, I deconvoluted the XRDs, and the different weight percentages are listed inside the table, and it is visible from the table that as the amount of oxalic acid increases, in all cases, an enhancement can be observed in case of in the amount of rutile phase of TaO2. But in the case of final samples, that means from S8 onwards, irrespective of the amount of oxalic acid, only rutile phase are there, because this high temperature give only the stable rutile phase of TaO2. And then the reflectance spectra, UV reflectance spectra of different samples are here. The third sample, C1, the sample C, it is visible that as the amount of rutile phase of TaO2 increases, spread can be observed more into the visible region compared to other samples. Then the nonlinear characterizations were carried out by the Z scan technique, and the Z scan, the peak, then the variation of normalized transmittance versus Z peaks are here for all the samples. In all cases, a negative nonlinearity is visible because there is a peak which is followed by valley in all cases. How the linear variation, the alpha linear absorption coefficient, how it varies with annealing temperature, it is plotted here. As the annealing temperature increases, an enhancement can be observed in the case of alpha, because there is an enhancement in particle size which helps to increase the value of alpha. And in the case of when we plot alpha against amount of oxalic acid for each annealing temperatures, the maximum, there is a change in all cases, but the maximum change can be observed in B and C, because in B and C there is a transformation from other phases to the rutile phase of TaO2. It is visible from B and C compared to A and D. But in A and D there is also an enhancement that is mainly due to the increase in particle size due to the agglomeration which occurred by the presence of oxalic acid here. Then the variation of N2 with the annealing temperatures are here in all the samples with a different amount of oxalic acid. In all the samples, N2 enhancement can be observed with the temperature. It's mainly because an enhancement in alpha is here. Alpha has a direct effect on N2 in case of thermal nonlinearity. That effect here. And in the case of when we plot the amount of oxalic acid versus N2 in different annealing temperatures, from this graph and also from this bar diagram, it is visible. In the bar diagram, second diagram, the maximum change in rutile phase is observed in 400 and 600. The same thing can be observed in N2 variation also. Maximum change in 400 and 600. There is also a change in 30 and 800, but that is mainly due to the agglomeration. The rutile phase effect can be mainly observed in 400 and 600 degrees Celsius, where there is a change in to the rutile phase of TaO2 from other phases can be visible. Then conclusion, the work detailed is an attempt to understand the effect of crystallographic phase on the thermal nonlinearity of TaO2. As the crystallographic phase changes more to the rutile form of TaO2, the linear absorption as well as thermal nonlinearity of the sample increases. That's all. Thank you.
Okay. Or can you say what is the novelty of your work? Because the same work has been published by so many people.
Yes, sir. The novelty is actually I did this work to extend it to the solar cell applications. Actually, in my PhD period, I did some solar cell works, but I used usual anodized TaO2 for the purpose to make the photoanode. But if by referring some purpose, I understood that this nonlinear absorption has a direct effect on HOMO-LUMO separation in solar cells. So by making this type of a tuning in optical nonlinearity, I can apply this to the solar cell area. That's the main work, but that's the future scope still. That's why I did this.
Okay. Then one more question. What is the difference between annealing and calcination? Here you use the annealing.
Calcination is just to heat the material, but annealing to vary its properties, and mainly I anneal that material in 1 hour or 2 hours inside the furnace. But in calcination, we just anneal and remove the sample from the furnace.
No, that is not the difference. You must know what is the difference. Okay.
Okay, sir.
Sir, Franklin, sir.
So how do you calculate the linear absorption coefficient?
That is from the emergent and incident laser intensities on the sample. Log I0 by I.
Oh, okay, the basic equation.
Yeah.
Okay, thank you.
Hello.
Yeah, you can start.
Good afternoon, one and all. I'm MCCK, Assistant Professor, Department of Chemistry, Mercy College, Palakkad. The topic of my presentation is crystallization of bioactive cobalt-based hybrid solids. In this work, we have synthesized two pseudopolymers of cobalt chloride to aminopyrrazine complexes by solvent evaporation method. A detailed structural analysis was done by means of single crystal XRD, FTIR, TGA, and elemental analysis. The role of non-covalent interactions that stabilize the crystal packing was investigated in detail using Hirschfeld surface analysis and 2D fingerprint plots. The solids were found to possess remarkable antibacterial activity as revealed by in vitro antibacterial studies and molecular docking studies. Self-assembly of organic inorganic hybrid solids
Can you
is
show the
primarily
respective
dictated.
slides?
Yes, sir. Hello.
Hello. Still at the title slide. You may change.
Oh, okay. Is it now visible, sir?
Yeah.
Introduction slide.
Okay. It is visible. Yes,
By
visible.
investigating the role of reaction parameters that affect the self-assembly process in the formation of polyoxomolybdate hybrid solids, we selected a heterocyclic ligand 2-aminopyrrazine as the organic precursor. However, it resulted in the crystallization of two metal complexes, which are pseudopolymers. Solids 1 and 2 were prepared by solvent evaporation method as per the scheme shown here. The obtained solids were characterized by single crystal XRD, FTIR. The thermal stability of the solids was studied by thermogravimetric analysis. From the single crystal data, it was observed that in the crystal structure of 1, CO2 plus is at the center of the octahedron, surrounded by 2 protonated aminopyrrazine moieties and 4 chloride ligands. Crystal packing in 1 is stabilized by hydrogen bonding interactions, leading to one-dimensional chains, which are further connected to form two-dimensional sheets, as shown in figure 4A and B. Apart from hydrogen bonding interactions, pi-pi interactions also stabilize the crystal structure. In the crystal structure of 2, CO2 plus is at the center of the octahedron, surrounded by 4 2-aminopyrrazine moieties and 2 chloride ligands. And unlike in 1, here the aminopyrrazine moieties are not protonated. In the structure of 2 also, there are extensive hydrogen bonding interactions, mainly NHCl interactions, leading to one-dimensional zigzag chains, which are further connected to form two-dimensional sheets. Inter and intramolecular hydrogen bonding interactions further connects the sheets to form three-dimensional network. In order to obtain a deep insight into various non-covalent interactions, Hirschfeld surface analysis were carried out. Hirschfeld surface analysis represents a novel approach for visualization of molecular surfaces and for investigating intermolecular interactions in crystals. And the presence of such interactions can be explained by mapping Hirschfeld surfaces on different properties such as d-norm, molecular electrostatic potentials, shape index, curvedness, etc. Figure 9 shows the Hirschfeld surfaces plotted on different properties, and 9A shows the d-norm surface of solid 1. And here, the bright red circular spots on the Hirschfeld surface indicates the regions involved in hydrogen bonding interactions. Similarly, in 9D, it is a shape index map. And on this, we can see adjacent triangular blue and orange patches over the aromatic ring, which indicates the presence of weak pi-pi interactions in the crystal. Curvedness is another important property represented in 9E, which indicates the planar nature of the molecules. We can also plot electrostatic potential map on the Hirschfeld surface of 1, and the red color regions indicates the electronegative regions, where the blue corresponds to the electropositive regions on the surface of 1. Figure 11
shows the Hirschfeld surfaces of solid 2, and 9A represents the denome surface, and 9D indicates it's a shape index map, which presents the characteristic features of pi-pi interactions in the crystal, and 11E shows the curvedness map, which indicates the planar nature of the molecule. Electrostatic potential map was also plotted on the Hirschfeld surface of 2. Another important information that is obtained from the Hirschfeld surface analysis is two-dimensional fingerprint plots. It provides a fingerprint of the intermolecular interactions in the crystal, and it gives information on the type of interaction and also the relative area of the surface corresponding to each kind of interaction. Figure 13 represents the fingerprint plots of 1, and in 1, the major contribution to the Hirschfeld surface is due to HCl interactions contributing to about 52.8% to the total surface, and that is appearing as two sharp symmetric spikes. Figure 14 represents the two-dimensional fingerprint plots of solid 2, and in this, the HH interactions are the most abundant, contributing to about 42.9%, followed by NH interactions. The prepared complexes were also evaluated for its antibacterial activity against various bacterial strains, and it was found that solids 1 and 2 showed remarkable antibacterial activity. Molecular docking studies were also carried out in order to substantiate the in vitro results of in vitro antibacterial studies. Docking studies were carried out using Autodock software, and the results were analyzed using BioVia Discovery Studio. The protein target chosen was DNA gyrase B present in E. coli and Bacillus subtilis. Figure 16 and 17 represents docking of solid 1 and 2 respectively with DNA gyrase B present in E. coli. Figure 18 and 19 shows docking of 1 and 2 with DNA gyrase present in Bacillus subtilis. The binding free energy values indicate the binding affinity of the prepared complexes with the protein target. The higher the negative value of the binding energy, the greater will be the binding affinity. So from the docking results, it was observed that solids 1 and 2 shows a higher negative value of the binding free energies with the DNA gyrase when compared to the free ligand, especially solid 2 with the protein target 4DDQ, that is a protein ID, with DNA gyrase present in Bacillus subtilis. So solid 2 showed a highest negative value of binding energy, that is minus 6.37 kilocalories per mole. To conclude, two cobalt-based pseudopolymorphs with two aminopyroxyl ligand were synthesized using solvent evaporation method. The role of non-covalent interactions that stabilize the crystal packing was investigated in detail using Hirschfeld surface analysis and fingerprint plots. The prepared complexes showed remarkable antibacterial activities when compared with the free ligand and the standard antibiotic gentamicin. In particular, 2 exhibited greater sensitivity towards all bacterial strains. Molecular docking studies were in good agreement with the results of the wet lab experiments. And from the in vitro and in silico studies, it can be concluded that the synthesized cobalt-2 complexes can be promising novel antimicrobial agents. Thank you.
So how do you do the antibiotic studies, and is there any, you didn't show any results from that one? Or
Actually, we measure the zone of inhibition. We measure this circular spots, no? So that's a zone of inhibition. We measure that zone of inhibition with a ruler and comparing the distances.
So did you calculate the MIC values from here, or?
No, we just did a preliminary screening. MIC values are not calculated.
How do you get this electrostatic potential surface diagram? Wow.
That is using software Crystal Explorer.
So do a docking simulation with what software do you use?
Docking was done using Autodock, and the images were rendered using another software, BioVia Discovery Studio.
Did you do any other in vivo or ex vivo studies, or you are planning?
No, that is pending, sir. We just this is just a part of my work, and only the in vitro studies have done.
Okay, is it? Are you doing PhD?
Yes.
Okay, who is your guide?
Dr. Jency Thomas, St. Thomas College, Thrissur.
Oh, okay, thank you.
Thank you, sir.
Okay, thank you.
Thank you, sir.
Good afternoon, all. Is my screen visible?
Yeah. Okay, you can start.
Okay. Good afternoon, all. Myself, Sinida B. Nair, Assistant Professor in the Department of Physics, Sri Shankara College, Kaladi. The title of my work is Fabrication of PCUO and TiO2 Nanotubular Heterostructure for Enhanced Photocatalytic Activities. The outline of my presentation comprises of introduction, highlights, experimental and characterization techniques, results and discussion, conclusion, scope of future work. Introduction. With the worldwide technological developments, environment and energy issues become a growing challenge to the existence of living beings. Various harmful organic pollutants enter the water sources and pose a serious threat to our environment. Photocatalysis is regarded as one of the most effective and environment-friendly technology that utilizes solar light effectively to remove organic pollutants from water. The conditions for a good photocatalyst are, it must have high surface to volume ratio that offers large absorption area, high light absorption efficiency to make use of the entire solar spectrum, effective separation of photogenerated charge carriers, biocompatibility, stability of the photocatalyst, and recycling capability. Semiconductors such as titanium dioxide, zinc oxide, iron oxide, etc. all act as good photoactive materials. Among us, TiO2 has proved its benchmark as a good photocatalyst due to its high photochemical stability, biocompatibility, non-toxicity, unique optoelectronic potential, etc. properties, etc. Among various nanostructured forms of TiO2 like nanoparticles, nanorods, nanofibers, etc., the research potential of one-dimensional nanotubular structure is significantly high since it offers excellent electron transport pathways for the vertical transfer of electrical charges along the length of nanotube. It offers excellent electron hole separation properties. It shows excellent morphological, optical, and electrical properties. The three most common polymorphs of TiO2 are anatase, rutile, and brucite. Anatase TiO2 is an N-type indirect bandgap semiconductor and is having a bandgap of 3.2 electron volt, which is used in charge separation devices like DSSCs and photocatalysis. However, due to its wider bandgap of 3.2 electron volt, it shows poor response to visible light absorption. Also, its fast electron hole recombination rate leads to poor quantum efficiency. Intense efforts have been done to shift its optical response to the visible range. Band structure modification by heterostructure formation is found to be the most promising method for improving the visible light harvesting. But the modification method found in literature are based on high thermal energy budget, costly, time-consuming, and usually suffer from multiple and tedious steps. Hence, simple and cost-effective methods in low energy budget is particularly important. Highlights of this work are heterojunction construction of PCUO and TiO2 constructed by electrochemical anodization followed by impregnation method. This modified structure offers advantages of tailoring of bandgap of the nanotube to visible region, achieved a 5-fold increase in the photocatalytic efficiency when compared to undoped tone. Figure 1 shows the process flow of formation of heterostructure of PCUO and TiO2 nanostructure. Well-loaded tones are fabricated by anodization of Ti foil in a 2-electrode system with ethylene glycol and ammonium fluoride as the electrolyte at room temperature. Then these fabricated tones are imbricated for 4 hours in a magnetically stirred solution prepared by adding copper sulfate to the aqueous solution of ethanol. The impregnated samples are annealed for 2 hours at 450 degrees Celsius in air to obtain the modified PCUO and TiO2 structure. These are the characterization techniques done. Moving to the results and discussion. First, morphological analysis. The micrograph reveals a perfect tubular structure for the tone. The surface morphology of the prepared CuO tone analyzed from FESUM indicates thickening of the boundary walls. However, the tubes are not blocked and the tubular structure is still retained. Figure 3 shows the EDAX spectrum and it contains Ti, oxygen, and small percentage of copper is incorporated in the sample. Figure 4 shows the XRD pattern of tone and CuO tone. The peak around 25.3 degree, 48.1 degree, 53.9 degree, and 68.7 degree correspond respectively to 101, 200, 105, and 116 crystal planes of anatase TiO2. In addition to this intense peak, low reflection peaks are observed around 35.6 degree and 48.8 degree in CuO tone structure. These are identified as the reflection from 002 and 202 planes of copper oxide. And it indicates the formation of both copper oxide and TiO2 phases. This is the optical studies. Diffuse reflectance spectroscopic analysis is done to determine the optical band gap of this sample. Optical studies in figure 5 indicates that a reduction in band gap from 3.2 electron volt of anatase tone to 2.36 electron volt for the modified structure. The current voltage characteristics of tone and CuO tone is shown in figure 6. Tones do not show any rectifying behavior, but CuO tone exhibit very good rectification. The significance of this PN heterojunction formation is in its ability to provide charge carrier separation. And it is seen from figure 7 that within the time span of 180 minutes, about 75% of photo degradation of methylene blue is achieved for the active solution. A maximum of 5-fold increase in the degradation rate for methylene blue is obtained with CuO tone than pure tone. And the enhancement in photocatalytic activity can be ascribed to 3 important factors: the creation of a PN junction that provides an internal electric field that helps in the separation of photo-induced electron hole pairs, increased absorption of visible photon due to the reduced band gap, and the creation of more active absorption sites by the small size of copper oxide nanoparticles and the large surface to volume ratio of the heterostructure. The photocatalytic mechanism is shown in figure 8. CuO tone respond to light radiation producing the electron hole pairs. The photo-generated electrons and holes are moved in the opposite direction at the junction and enable effective separation of the electron hole pairs. The potential barrier at the junction help in building a space charge separation for the longer time. The electrons on the end TiO2 react with O2 absorbed on the surface to form the superoxide radical, whereas the photo-generated holes left in the valence band react with water molecule to yield highly oxidative hydroxide radical, which is a strong oxidizing agent to decompose the dye. This reactive radical combined with organic compounds to form carbon dioxide and water. Moving to the conclusion, this work focuses on the fabrication of PCuON TiO2 type 2 heterostructure by simple, cost-effective, and time-saving electrochemical anodization followed by impregnation method. Prepared CuO tone shows superior photocatalytic activity for methylene blue due to its lowered band gap energy and increased charge separation. The rate of photocatalytic activity of PCuO and TiO2 is 5 times greater than that by the pure tone. Scope of the future work. This study lays the foundation for many future work that can develop highly efficient photocatalysts. The band gap tuning and conductivity enhancement presented in the work make them potential candidate for other energy and environmental applications like water splitting, DSC supercapacitors, etc. The prepared techniques employed in the current study can be directly applied to other application areas as well as to other metal oxide semiconductors. Thank you.
Okay, your work is good. Then the question is, why did you choose only methylene blue for photocatalyst studies?
As the next part, I want to try for other dyes, etc. Sir.
Okay.
With methyl orange, Congo red, etc.
Okay.
For this work, I tried only this methylene blue.
Then, how did you study the photocatalysis?
I prepared this methylene blue dye and put this sample in the methylene blue dye and placed under this sunlight for 3 hours. For different times, that is for 15 minutes, 30 minutes, 60 minutes, 120 minutes, and 180 minutes for different time.
Okay, what is the intensity of sunlight?
That I
okay.
think it's a
as a physicist, you must ensure that the intensity should be stable.
Okay, sir.
Okay, 180 minutes. That much is the highest value. Okay. Sir, can you please?
What do you expect? So this, you have observed methylene blue degradation. So can this be used as a DNA intercalator, chelating agent, something like that? Do you have any idea?
No idea, sir. Sorry, sir.
Okay, thank you.
Okay. Thank you very much, sir.
Okay, thank you.
Okay, ma'am. Thank you.
Good evening, ma'am. Am I audible, ma'am?
Audible.
Thank you, sir. Once again, good evening, everyone. I am Vinita N, presenting the current work under the guidance of Dr. Minikrishna K from Department of Physics, Vimla College, Thrissur. The topic of study is on the structural and optical characterization of zinc aluminate nanoparticles synthesized via green microwave road. Zinc aluminate, which is the material of present study, has many advantages like high chemical stability, high quantum yield, good fluorescence efficiency, strong thermal and mechanical resistance, wide surface area, low surface acidity, and also it is a direct bandgap semiconductor with a bandgap of 3.8 electron volt, and it is useful in dielectrics, optics, and sensors, and many other applications. But the high temperature synthesis and the use of very toxic chemicals limits its industrial applicability and make it very expensive. Here lies the importance of green synthesis. Actually, the advantages of green synthesis are it is very environment friendly because it replaces the use of toxic precursors, and also it improves the monodispersive nanoparticles, modulates size and shape, and also it reduces the time for synthesis at a very low cost. Here, plant extracts are the main thing which serve as reducing agents for metal cations and also stabilizes the synthesized particles. Now we will move on to the experimental procedure of the present work. Here the precursors used are zinc nitrate and aluminum nitrate, which are mixed, and to that mixture a plant extract, which is the extract of freshly cut open-shade aluminum leaves, is added, and it is heated in a microwave oven with these given specifications. Actually, I have prepared 4 samples with the 4 different precursors ratios. The duration of synthesis is lowered to just 10 minutes. And now moving on to the results. First, I have done the XRD analysis in order to check if the structure is formed or not. And the equipment which is used for the XRD analysis is Bruker D8 Advanced X-ray diffractometer. And the as prepared samples show spinels, peaks corresponding to the spinels in aluminate, even without post annealing, but it is not perfect. So in order to make it completely spinel structure, we have to do firing, that is calcination. Also, the distinctive spinel peaks corresponding to zinc aluminate, which loses its intensity on increasing the zinc content. To substantiate XRD results, FTR spectra is also done with the Shimozu air spirit spectrophotometer, and there is a band which is at 533 cm⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ actually corresponds to the yellow-6 group, which builds up zinc aluminate spinel, and also the peak becomes the peak becomes stronger with the decreasing the zinc amount. And also we can see a peak at 1370 centimeter raised to -1, which is corresponds to the NO2 group, which may be due to the existence of leftover plant extract, since our sample is not calcined. And the bands which appear in the range 700 to 1000, which will be correspond to the organic molecules which is left over in the sample. And also the samples with a less zinc amount shows much intense peaks. And in order to find out the band gap, we have done the DRS spectral analysis, and we can observe a shift, blue shift from the bulk band gap energy, that is 3.8 electron volt is observed here. These are the band gap values corresponding to all the 4 samples, and the sample with the high zinc content have a band gap in the range 3.04 electron volt, which is corresponds to the zinc oxide, which is present in the sample. And also there is some fluctuation in the band gap energy, which may be due to the quantum confinement effect, because the band gap drops as crystallized size grows. And also there are some shoulders in the DRS spectrum, which may be due to the lattice faults. And now coming to the photoluminescent analysis, we can see UV and blue emission at an excitation of 300 nanometer, which is a typical property of undoped zinc aluminate, which is the best photoluminescent response is observed for the sample with the less zinc content. And also this is substantiate the structural analysis, XRD and FTR. Now, in order to check whether the formation is happening on calcination, we have calcined one sample, which is the first sample, that is with low zinc content. We have calcined the sample at 450 degree for 2 hours, and as expected, the presence of all prominent spinel peaks of zinc aluminate is observed here, which is well agreement with the standard data. And here average crystallized size is calculated. It is as 4.428 nanometer, which is using the Debye-Scherrer equation. In order to confirm this structural formation, we have done the TEM analysis, and from the TEM analysis, the lattice parameter is calculated. And these are the conclusions of the present work. The present work, microwave assisted green synthesis, which is found to be very reliable and cost effective for producing nanocrystalline zinc aluminate. And the advantage is that the synthesis duration can be drastically reduced. And also the spinel formation on calcination at a very low temperature, that is 450 degrees Celsius, we can form the spinel at this very low temperature, which is confirmed from XRD and TEM measurements. And also the structural analysis are supported by PL emission, and also from the DR spectrum, we have got a very good band gap, that's 4.85 and 5.2, 5.04 in the range, 4.85 to 5.04. The band gap tuning is possible and it is very useful in optical device band gap engineering, and the post annealing improves the crystallinity. And these are the references supported this work. And we thank DST Phys Lab, Postgraduate Research Department of Physics, Vimala College, Thrissur. And I personally thank KSCSTV for the research fellowship. And thank you so much.
Okay, what is your source of this plant extract? From what?
Sir, the plant extract is actually from Opensia dialinine plant juice.
So you will have many many type of molecules, ions inside the plant extract, including lipids, proteins, and everything. How do you make sure that a particular material from your plant extract is doing this reduction to form this nanoparticle?
Sir, actually, we have to study the extract by phytochemical reactions such that actually the work is pending, sir. I have to study more about plant extract, why it is making this this kind of work.
Okay, this type of extracts, I mean, exactly this extract was used, reported in literature?
Yes, sir. Already it is reported in synthesizing some silver nanoparticles and some aluminum nanoparticles, etc. So I have tried this extract for synthesizing my material.
What is the particle size which you observe from TEM analysis?
So this is the results from TEM analysis, and this is the value of lattice parameter. It's in good agreement with the JCPD's value.
Average crystalline size 4.424, 428.
Yes, sir. Yeah.
Okay, thank you.
Okay, why did you choose 450 Celsius or your
Sir, actually, I
calcination
had
temperature?
yes, sir. Actually, I had done the TGA DT analysis before for the sample.
But you didn't mention anything about TG analysis?
Sir, actually, that was my previous work, so I have not included it here. I actually have tried 4 different temperatures for the post annealing, and also I have done the TGDT analysis. From that, I have fixed this temperature.
Okay, thank you.
Thank you, sir. Sir, can I leave?
Yeah, you can.
Thank you, sir.
Good afternoon, sir. Can I share my screen?
Yeah. You can continue.
Is my screen visible?
Yeah, visible.
Okay. Okay. Today, I'd like to present on my topic, zinc tungsten reduced graphene oxide composites for the electrochemical sensing of dopamine. And me, myself, Meenu Veldos, research scholar, Department of Chemistry, Newman College, Thodupuzha, and under the guidance of Dr. Singh C. George and Alex Joseph. And here I have chosen this material, that is zinc tungsten. Why zinc tungsten? It's because of its optical properties, high electrocatalytic activity, good magnetic and electrical properties, improved sensitivity and response time, facile synthesis, photocatalytic and luminescent properties. All these properties have attracted me towards this particular material. And in addition to that, there are, to enhance the property of zinc tungsten, different strategies such as modulating crystallinity, tuning morphology, and ion doping, etc., has been done so far. So by here, I have done or modified the zinc tungsten by using reduced graphene oxide. And by adding reduced graphene oxide or to this material, it will increase the surface area and thereby results in more active site in the electrocatalyst. And here I use dopamine as an analyte for sensing application, because dopamine is an organic molecule which is essential for the proper functioning of central nervous system and hormone balancing. In addition to that, deficiency may cause low levels of dopamine may cause Parkinson's disease or other diseases as well. And the electrochemical sensors are best for sensing dopamine because it is an electrochemically active molecule, and the electrochemical techniques are considered to be simple and as well as very sensitive in nature. Abstract. Here, I have synthesized zinc tungsten reduced graphene oxide and zinc tungsten reduced graphene oxide composites. And the corresponding characterization was done by using XRD, FTER, STEM, TEM, and Raman analysis. The electrochemical activity of zinc tungsten and reduced graphene oxide as well as these composites was also checked towards the dopamine sensing. And the synthesis procedure which I have employed for the zinc tungsten include: the synthesis was carried out by aqueous solution growth or precipitation method, and about 5 millimole of zinc acetate and corresponding sodium tungsten was dissolved separately in about 30 ml of water separately, and after that it is mixed together under constant stirring for an hour, and the resulting white precipitate was obtained, and it is then washed and dried properly to obtain the sample. Synthesis of reduced graphene oxide, and the graphene oxide was prepared from exfoliated graphite powder by modified Hammer's method, and yellow precipitate of graphene oxide that's obtained was washed several times with distilled water and HCl in order to make it neutral. And the neutral solution of graphene oxide was then treated with 100 millimolar sodium borohydride solution and is magnetically stirred for about 3 hours. And the black colored precipitate was then washed with the distilled water and dried to obtain the reduced graphene oxide. Then how the synthesis of zinc tungstate or graphene oxide, reduced graphene oxide composites was done. It is explained here. And the different compositions of RGO means about 4% as well as 2% we have prepared, was prepared by weighing the composition of reduced graphene oxide. And moving on to our result and discussions. Here I have shown the XRD of both zinc tungstate and zinc tungstate RGO. I have only included the 4% result of XRD because that is much more electrochemically active. So here, first one represents zinc corresponding XRD pattern obtained for zinc tungstate, and second one represents that of XRD picture obtained for zinc tungstate RGO reduced graphene oxide composites. And it is clear that the intensity, the clear-cut intensity of zinc tungstate has been reduced, as well as the crystallinity is also changed to some amorphous character. Here we are modifying with about 4% of RGO at the maximum. So in addition to that, an extra peak has been appeared, shows for this reduced graphene oxide at a 2 theta of about 23 degree. And moving on to FDR, and since this A, B, and C represents the Fourier transform infrared spectroscopy for zinc tungstate RGO composite, and reduced graphene oxide respectively. And here all the peaks for all peaks are almost the same for both. That is, this RGO shows a band at 3,500 because of hydrogen bonding, and similar is the case with that of zinc tungstate, because here we are synthesizing this material in aqueous solution, so it will also shows a particular peak, means FPR peak at 3,500 something range. And this is a Raman analysis spectra which I have got for zinc tungstate RGO and corresponding zinc tungstate RGO composite. It is more clear that a composite formation has been done. It is clear from this Raman analysis, that is for the zinc tungstate it has only one peak, and for RGO both the D and G bands is also present, and for zinc tungstate RGO composites both the composite pristine zinc tungstate peak as well as the peaks of RGO were also found here. And these are the same images, and from the same images there is no such no much information can be arrived, but we can see the coating, means the dispersed it is dispersed on the surface of RGO. And this is the EDAX pattern analysis of zinc tungstate and zinc tungstate RGO 4%. And it is clear that here for zinc tungstate, the elements zinc, tungsten, oxygen, etc. were present. But in the case of zinc tungstate RGO composite, here the carbon as well as the oxygen is also present. In addition to that, the intensity has also slightly increased. And this is the elemental composition of from the EDAX pattern. And these are the TEM images, and this is for the zinc tungstate alone, and this is for the RGO alone, and this is for the composite. And it has been seen that it is spread on the zinc tungstate nanoparticle has been spread on the surface of this graphene oxide, reduced graphene oxide. Then for electrochemical sensing, here we are using carbon paste electrodes as for coating. So we have prepared the carbon paste electrodes in our lab, and the graphite powder is mixed with paraffin oil in 7:3 ratio, and is ball milled for about 72 hours. And the carbon paste so prepared was filled in a glass tube at a height of around 1 centimeter, and the silver wire was inserted for the electrical contact. The CP electrodes was chemically modified using pristine zinc tungstate RGO and zinc tungstate RGO 2% and 4% respectively. And the corresponding electrochemical studies were done. And this represents a CV of Bayer zinc tungstate and zinc tungstate RGO 4% and 2% and 4% respectively. And this was done by using acetate buffer with a pH of about 4.8, and dopamine was used at analyte, and the concentration is about 0.01 molar. And in addition to that, KNO3 is 0.1 molar KNO3 is a supporting electrolyte, and the potential window ranges from -0.7 to +0.7 volt, and it is done at a scan rate of 0.1. And before moving on to the previous studies, it is necessary to fix the pH of that particular solution for getting the maximum peak height. So the pH studies were also done by using DPV technique. And so from this figure, it is clear that from this profile, it is clear that the pH is pH is 4.8, has a maximum current. So we have fixed pH as 4.8 for the upcoming studies. And this is a DPV analysis of CPV, zinc tungsten RJ 4%, because I have done the DPV analysis of 4% alone, because in the graph of CV, the 4% shows the maximum peak height. And the DPP analysis was done by using this particular CPE, zinc tungsten RJ 4% composites only. And here the DPP represents a composition ranging from 0.1 millimolar to 0.01 millimolar dopamine in the presence of 0.1 molar KNO3 as the supporting electrolyte in a acetate buffer of pH 4.8, and a potential varies from 0.15 volt to 0.6 volt. And the corresponding linear fit graph were also obtained, and Pearson's as well value was obtained about 0.9967. And the most probably interference studies should be necessary for carrying out the sensitivity of a particular composites, sensitivity of composites towards various analytes such as ascorbic acid, glycine, creatine, glucose, etc. All these parameters were present in our blood serum. So it is necessary to analyze how these will affect the sensing ability of that particular one. So we have done the interference studies by taking 1:0.1 equivalent of dopamine and corresponding interfering species, and the analysis were carried out, and ascorbic acid seems to be the most interfering, and almost all others are seems to be about interfering, because they they are actually affecting the peak height of the particular composites. And the major conclusions which I have arrived is that in the present work, we fabricated a non-enzymatic low-cost electrochemical sensor for the detection or electrochemical detection of dopamine. And the synthesis was very simple, and because it is carried out by using zinc tungsten RJ composite, was carried out using co-precipitation method. And physiochemical properties of this pristine tungstate and reduced graphene oxide and zinc tungsten composites was carried out using XRD, Fourier transfer, TER, scanning electron microscopy, and TEM and Raman analysis. And the electrochemical analysis was done by using PV and EPV techniques, and it shows excellent activity towards the detection of CA and shows high sensitivity with a correlation coefficient of R² of 0.9967. And these are the references which I have used for this. And I sincerely acknowledge all my team members, as well as especially my guides, Dr. Sinsi George and Dr. Alex Joseph, for the wholehearted support given to me. In addition to that, I would like to acknowledge the financial support from the MG University Kottayam in the form of University JRF Fellowship for the work. And thank you.
Thank you. It was nice work. Did you compare the non-dopamine sensors, which is already a non-influencer with what is your
one second. Actually, I'm planning to do, whether it is possible, I don't know. I'm planning to do a real-time analysis. So I have compared with calculated the LLOD, and it has been about 4.63 micromolar, which is in best result as it is not reported so far.
Okay, did you check the possibility of these compounds in passing the blood-brain barrier, because dopamine sensing?
Sir, actually, I haven't checked it now, but I would like to check it, or I'd like to do the real-time sensing if possible. I'm detailing about that.
Okay, thank you.
Okay, thank you. Let us go for the next presentation.
Hello. Hello, sir, I'm audible?
Yes, we can see the slides, but it's not moving.
It's not moving. Okay, so 1 second.
Okay.
So whether it is in slideshow mode or it is in.
This is also fine. You can go forward.
So now it's okay?
Yes.
Yeah, it's okay.
Yes. Good afternoon, everyone. Myself, Drishyavi, research scholar working under the guidance of Dr. Lakshmi C, Professor, Department of Chemistry, NIT Calicut. My work include ethmophenylalanine-based fluorimetric and colorimetric dual-channel probe for the detection of Ap3 plus and Cu2, detection of Ap3 plus, Cu2 plus, and F minus. So coming to our main focus is on the fluorimetric sensors or fluorescent sensors. Moving to the fluorescent sensors, what is a fluorescent sensor? As
Can
we
you
know,
move on to the next slide?
so it's not moving?
Not moving.
Oh, sorry, sir.
Okay, now it's okay. Okay, carry on.
Okay, sir. Now it is moving, right, sir?
Yeah.
Okay. So a molecular sensors, coming to molecular sensors, a molecule which can undergo or which can produce a readable signal on interaction with various analyte either through host-guest interaction or any chemical transformation
We cannot see the slide. We can only see the text introduction.
You just click on the
Yeah.
Now it's okay, sir.
Now it's okay.
Okay. A sensor is a molecule that can produce a readable signal on interaction with various analyte, either through host-guest interaction or chemical transformation are called as a molecular sensors. Coming to fluorescent sensors, these fluorescent sensors can be classified into chemosensors and chemodosimeters. And the sensors which undergoes reversible sensors which reversibly interact with various analyte to produce a readable signals are called as chemosensors. Normally, a chemosensor consisting of a signaling unit and a recognition unit connected through a linker. The emission profile of the signaling unit is controlled by the interaction of this recognition unit with a specific analyte. So in this example, we can see that the interaction of this recognition unit with a specific cation control the emission profile of the signaling unit. And coming to the chemodosimeters, the sensors which irreversibly undergo a structural modification in presence of various analytes are termed as chemodosimeters. So in chemodosimeters, it is mainly based on the reaction-based mechanism, and these are two examples of chemodosimeters. And we are mainly focusing on fluorescent sensors. Various analytical detection techniques are developed for the selective and sensitive detection of various analytes have evolved, which include atomic absorption spectroscopy, flame atomic absorption spectroscopy, inductively coupled plasma mass spectrometry, etc. But these techniques are expensive, complex, require trained personnel, and need laborious sample preparation. But nowadays, fluorescent detection technologies have gotten greater acceptance due to its good selectivity, sensitivity, quick response, and low cost. So we are focusing mainly on the fluorescent-based molecule for the detection of various analytes. So as we know, the heavy metal ions plays a crucial role in different biological process, and the strict regulation of their concentration require the proper functioning of any organism. Any deviation from the permissible level in their concentration can lead to different physiological condition. Among these heavy metal ions, iron and copper plays a very important role in different biological process. Iron helps in the formulation of hemoglobin, muscle activity, immune system development of brain and brain development and functioning, thyroid functioning, oxygen uptake and metabolism, electronic transfer, synthesis of DNA and RNA, nervous conduction, proton transfer, enzyme synthesis, etc. The iron deficiency adversely affect different parts of the body, include heart, brain, stomach, etc. Similarly, copper also help in the growth, immunity development, digestive system, proper functioning of digestive system, and as a part of antioxidant, and is helping the proper functioning of nervous system also. And the copper poisoning also adversely affect different parts of the body, include liver, eye, skin, kidneys, mouth, circulatory system, etc. So the development of fluorescent sensor for the selective and sensitive detection of these heavy metal ions are of most important. Hence, we designed 4 FMO-phenylalanine based chemosensors for the selective and sensitive detection of Fe3+ and Cu2+. The designing of this molecule consisting of connecting FMO-phenylalanine to either naphthalene or pyrinamine through amide or amide triazole linkage. Then the synthetic route involves the EDC coupling of the FMO-phenylalanine with the corresponding amine, that is naphthyl, pyrene, or propylamine, to yield the corresponding amide-linked derivative. The propyl derivative under click condition to produce the corresponding amide triazole-linked derivative. Then we have recorded the both absorption as well as emission spectra of all the 4 compounds, and both the naphthyl derivative exhibited similar absorption as well as emission spectra. Similarly, both the pyrene derivative also exhibit similar absorption as well as emission spectra. All the 4 probes respond similarly towards various analytes and various conditions. Here we are using FPAPY as a representative example. Then we have performed the selectivity experiment towards Fe3+ and Cu2+. We recorded the fluorescent response of these molecules in various metal ions in presence and absence of Fe3+ and Cu2+. In presence of the fluorescent intensity of the probe conscious only in presence of Fe3+ and Cu2+, and other metal ions are failed to elicit such changes. And also any other okay, these are the corresponding photographs of FPAPY in DMSO containing various metal ions under 365 nanometer UV lamp and under normal light. Here we can see that the fluorescent intensity of the probe conscious only in presence of Cu2+ and Fe3+. So then moving to the fluorimetric and colorimetric titration experiments, here we can see that with the gradual addition of Fe3+ or Cu2+ to the probe solution, the intensity of the probe decreases gradually. So then we calculated the limit of detection, and the limit of detection of FPAPY towards Fe3+ was found to be 1.88 micromolar, and that towards Cu2+ is found to be 3.12 micromolar. Then we have performed a colorimetric titration experiment with a gradual addition of Fe3+ or Cu2+ to the probe solution. The absorbance of the probe increases gradually. So then we have performed the Stern-Volmer analysis and Jobs plot analysis. Then Jobs plot analysis revealed that all the probe prefers a 1:1 binding to Fe3+ and Cu2+. Further, we analyze the utility, or further we investigate the utility of probe Fe3+ for the detection of fluoride ion. As we know, the fluoride ions are known to form a thermodynamically stable FeF or resulted in the emission quenching of the probe. Any decomplexation with the formation of FeF6 3- with the addition of fluoride ion to the probe Fe3+ complex may resulted in the restoration of the fluorescent intensity of the probe. So this is a photograph of FPAPY Fe3+ complex containing various anion under 365 nanometer UV lamp. As we from the figure itself, it is very clear that only in the presence of fluoride ion, the emission intensity of the probe regains. Then we have performed the fluorimetric titration experiment, and we added fluoride ion source to, we gradually added fluoride ion to the probe Fe3+ complex, and it's very clear from the figure. The emission intensity of the probe increases gradually with the addition of fluoride ion, and the limit of detection was found to be 0.64 micromolar. Further, in order to confirm the decomplexation mechanism, we have performed the colorimetric titration experiment. With the gradual addition of fluoride ion to the probe Fe3+ complex, the absorbance of the probe decreases gradually, suggesting the decomplexation mechanism. Then we have performed the reversibility studies with the alternate addition of Fe3+ and fluoride to the probe solution. We recorded the emission spectra. With the addition of Fe3+, the intensity of the probe decreases, and with the addition of the reversal happens with the addition of fluoride ion. This cycle is repeated in an alternative manner and confirm the reversibility of this probe. Then practical utility of the probe was demonstrated by coating the probe on solid surfaces and the prop coated filter paper is used for the quick screening of Fe3 plus Cu2 plus and fluoride ion. These are the corresponding fluorescent photographs of filter paper strip before and after treatment with the respective salt solution under 365 nanometer UV lamp. In conclusion, we have designed, synthesis, and characterized 4 ethmophenylalanine-based fluorophores. Preliminary photophysical properties of this molecule in solution state were evaluated. All the 4 fluorophores shows a quenching behavior in presence of Fe3 plus and Cu2 plus ion with good selectivity and sensitivity. And the limit of detection of all probe towards Fe3 plus and Cu2 plus was found to be in the lower micromolar range. And all the 4 probe prefers a 1:1 binding stoichiometry towards Fe3 plus and Cu2 plus. The probe Fe3 plus complex can be used as a sensor for the detection of fluoride ion in solution state via Kanon fluorescent mechanism. Thank you.
Thank you. It was a nice work.
Thank you, sir.
So what is the role of this naphthyl moiety when you have a phenyl FMOC group already there? Don't they do quenching in between?
No, actually, sir, we need one binding unit for sensing any metal or any anions. So FMOC itself can't bind. Also, we can increase the
What
fluorescence
kind of
of
binding
this
is it? Is it stacking interaction or is it electrostatic interaction or?
So it's a kind of host-guest interaction, that is coordination type of interaction.
Oh, okay. But you have, in fact, the FMOC group and naphthyl both are potential fluorophores, right?
Yes, sir. It is just to increase the fluorescence of this probe, we are incorporated this pyrene and naphthalene unit.
Okay. So the synthesis is also already reported in publication, right?
Same molecule is not reported, sir. The synthetic route is already published, but the same molecule is not yet published.
Okay, okay, great.
Thank you, sir.
Thank you.
Okay, thank you.
Thank you.
Is not available. Okay. So go for the next. Okay, you can start. No voice.
Your sound is mute.
Sometimes problem with net. Somewhere, please start. Can we move on to the next presentation? By the time she has to correct her problem. Yeah, that's financial.
Am I audible now?
Yeah.
Is my screen visible?
Yeah, visible.
Good afternoon all, and welcome to my presentation on thermal diffusivity measurement of Fe2O3 AU nanofluid composite using thermal lens technique. Myself Divya Rajan, Research Scholar in Physics, St. Teresa's College, Ernakulam, under the guidance of Dr. Shanti A. My presentation is structured as follows: introduction, synthesis, characterization, thermal diffusivity study, results, and conclusions. Thermal diffusivity is a material-specific property which describes how quickly the material reacts to change in the thermal environment. Thermal diffusivity has significant role in heat transfer devices, in coolants, and in cancer treatment. A high value of thermal diffusivity is an indication of effective heat transfer through the medium. The findings that solids have higher thermal conductivity than liquids paved the way to a new class of heat transfer fluids called nanofluids, where nanoparticles got properly dispersed in a base fluid. There is a possibility for enhanced heat transfer through the nanofluid because of the special thermophysical properties due to the presence of the nanoparticles. So here, we are focusing on a thermal diffusivity measurement using a novel nanofluid composite. When we think about nanoparticles for preparing nanofluids, it will be more advantageous to prefer nanocomposites, which has got combined physicochemical properties of the multimaterials with potential applications. Gold nanoparticles are so special because of their surface Plassmann resonance and attractive optoelectronic properties. As gold is an expensive metal, it is feasible to think about a companion which is less expensive, still has significant applications. Definitely, iron oxide can serve as a promising candidate, which is economical, non-toxic, biocompatible, and environmental friendly to be paired with gold for advanced applications. So we have synthesized a nanofluid of iron oxide and gold by a simple wet chemical method, where iron oxide, chlororic acid, and trisodium citrate were used to form a nanocomposite of Fe2O3 AU. The synthesis technique is depicted in the figure, which explains the chemical reduction process to form the nanofluid composite. After synthesizing, we have confirmed the formation of nanocomposite through various optical, morphological, elemental, and structural characterization, of which a few are to be discussed here. This is the UV visible absorption spectrum of the nanocomposite. Iron oxide exhibits a broad UV visible absorption. The peak at 352 nanometer result from the ligand to metal charge transfer transition of iron oxide. And the significant peak at 525 nanometer can be attributed to the plasmonic peak of gold nanoparticles. Morphological characterization of the sample was done through EFESM. The image shows a nearly spherical, still non-uniform distribution of particles in the composite. EDAX spectrum also confirmed the presence of iron, oxygen, and gold in the prepared sample. After getting confirmation regarding the formation of nanocomposite, we have done the thermal diffusivity study. Thermal diffusivity of a nanofluid can be measured using different techniques, of which thermal lens is one of the most advantageous for measuring the photothermal parameters during heat transfer. It is a high sensitive, minimum sample required, accurate, non-contact, and non-destructive technique. Lasers makes it possible to observe and understand certain phenomena which were otherwise not feasible using ordinary source of light. Laser-induced photothermal technique is a very sensitive technique which can measure even very small refractive index changes across the beam width resulting from temperature variation. A laser beam can thermally induce refractive index changes, which is the fundamental principle behind thermal lens spectroscopy. A Gaussian beam, that is a laser beam, is incident on a sample, which will excite the sample, resulting in non-radiative relaxation. Thus, heat will be generated inside the material, which is found to be maximum along the axis of the cylindrical beam waist. As a result, the temperature generated will force the molecule of the material along this axis to move towards the periphery. The spreading of molecules result in a change in the refractive index, which will result in the formation of a lens-like optical element termed as thermal lens. If a concave lens is formed, we can observe a thermal blooming through a detector. This can be used to investigate the thermo-optic properties of the sample, which is called the thermal lens technique. This is the block diagram of the thermal lens setup, and below given figure is the setup which we have used in our lab. We have used a dual beam pump probe mode match technique for this experiment. That is, the generation and detection of thermal lenses achieved separately by the pump and the probe. In mode match technique, both the beams are found focused by the same lens so that the radii of the pump and probe beams are similar within the sample. We have used a DPSS continuous wave laser of 488 nanometer with maximum power of 50 milliwatt as the pump for the generation of thermal lens. And the detection was done using a helium neon laser, which is of 632.8 nanometer for detecting the output. Required neutral density filters were used to lower the power of both pump and probe to avoid spherical aberrations due to the interference in the transmitted beam at high powers. Both pump and probe are made collinear in the mode matched configuration so that the beams propagate coaxially, which can create longer interaction length and better sensitivity. A mechanical chopper is used to modulate the pump beam intensity, and the changes in the probe beam intensity were monitored through a photodetector, which is connected to a DSO. The photodetector gives the intensity of the output probe laser beam, which is given by the decay equation given here. Thus, the time-dependent intensity is measured and fitted to get the intensity profile. Then the time response of the thermal lens can be used to determine thermal diffusivity using the equation D is equal to omega f square by 4 Tc, where omega f is the beam spot size and T is time constant. Figure shows a typical thermal lens obtained in the DSO. We have standardized the experiment using water, whose thermal diffusivity is obtained as 0.143 into 10 raised to minus 6 meters per second, which matches thermal diffusivity of the nanofluid. Here, the first figure shows the decay curve of 0.15 ml of nanofluid from the intensity versus time graph. And second graph is the thermal diffusivity versus concentration graph of nanocomposite at various concentration per 3 ml of base fluid. it is clear that the thermal diffusivity shows an enhancement initially, which is about twofold of that of base fluid at a particular concentration in our experimental range. After that, it shows a decrease, even which is better than the base fluid. The initial enhancement can be explained using Brownian motion, where the convection in liquids induced by Brownian motion of nanoparticles enhances diffusion. After a particular concentration, there is a possibility for cluster formation due to van der Waals attraction, which can reduce the molecular distance and causes a reduction in diffusivity. Here are the conclusions. We have successfully synthesized iron oxide gold nanofluid composite, and the formation is confirmed through various characterization techniques. Thermal diffusivity study showed a specific pattern of an enhanced thermal diffusivity at a particular concentration, from which we can find an optimum value for maximum thermal diffusivity. Here are the applications in high-performance thermal transfer liquids, in thermoelectric coolers, and in cancer treatment like photodynamic therapy and magnetic hypothermia. These are my references. Thank you.
Okay, here you have some applications. But
yes, sir.
To undertake any application study?
Sir, we have done the photodynamic therapy study of this nanocomposite, and it is found to be applicable in photodynamic therapy.
Okay. Then what is the novelty of your experiment?
Actually, thermal diffusivity measurements using single nanoparticles have done, but the main focus is always on thermal conductivity measurement. But most of the time, we may not be obtaining the actual values as expected. So, if we can measure the thermal diffusivity instead of thermal conductivity, then we can a transient heat conductivity measurement can be possible. And also using this nanocomposite, not much work is done so far.
Okay, okay. This is the first measurement.
Regarding this composite, I haven't found any other paper, sir.
Okay. Franklin, sir.
Thank you.
Okay. So for the next.
Okay, sir. Thank you.
So may you please unmute your mic.
Sir? Am I audible?
Yeah.
My presentation studies on the effect of terbium doping on the structural and optical properties of lanthanum tungstate nanoparticles. Myself, Soumya Kuriakos, doing research under the guidance of Dr. Thomas Verghese, Newman College, Thodupuzha. The objective of this presentation is to explain the synthesis of pristine lanthanum tungstate nanoparticle and terbium doped lanthanum tungstate nanophosphor by chemical precipitation method, and also to investigate the effect of terbium doping on the structural and optical properties of the synthesized nanoparticles by using various characterization techniques. Next slide. The rarer based tungstate have an important role in the display field and lighting device because of their abundant emission colors and other unique structural and optical properties. Lanthanum tungstate nanoparticles have monoclinic scheelite-like structure, and the terbium ion is used as dopant here. They are most widely used green emitter in the doped substances. By tuning the size, shape, and composition, the materials having new desirable properties can be explored. These are the characterization techniques we use. The structural properties of samples were studied using X-ray diffraction techniques and scanning electron microscopic techniques. Energy dispersive X-ray spectroscopy reveals the elemental composition of sample. Optical properties of the prepared sample were analyzed using UV visible absorption spectroscopy and photoluminescent spectroscopy. About the synthesis, we synthesized pure and 5 mole % terbium doped lanthanum tungstate nanoparticle by chemical precipitation method. For this, analytical grade chemicals such as lanthanum nitrate hexahydrate, sodium tungstate dihydrate, and terbium nitrate hexahydrates are used. In this presentation, pristine sample is termed as TB0 and doped sample is termed as TB5. Then move on to the sample preparation. This is the schematic representation of the synthesis procedure. Initially, 0.1 molar solution of lanthanum nitrate and sodium tungstate were dissolved in 100 ml of distilled water separately. The sodium tungstate solution was added to the lanthanum nitrate solution under constant stirring for 15 minutes at room temperature and allowed to precipitate. The unreacted agents were removed from the precipitate by washing with the distilled water several times. The obtained precipitate washed and dried at 70 degrees Celsius for 25 hours using hot air oven. The obtained product was calcined at 700 degrees Celsius for 3 hours in a muffle furnace to get in crystalline form, then grinded in using an agate mortar to obtain in the powdered form. And it is termed as TB0. For the preparation of doped sample TB5, lanthanum nitrate and terbium nitrate together taken as 0.1 molar solution, and the same synthesis procedure is followed. The XRD pattern of the pristine as well as terbium doped sample is shown here. The standard pattern is also given for comparison. The observed peak positions of the pure sample TB0 was well matched with the standard pattern JCPDS card number 82/2068, and it has chelate monoclinic phase with the C2/C space group. And the diffraction pattern of the doped sample was also well matched with the monoclinic phase. No additional peaks corresponding to terbium or any other impurities were observed. But, next slide. But the main peak positions of the doped sample is slightly shifted towards the higher diffraction angles due to the incorporation of the terbium ions into the lattice. Correspondingly, a small decrease in the terbium, a small decrease in the interplanar spacing values are observed in the terbium sample, and it is tabulated in the given table. The average crystallite size and calculated by the well-known Debye-Schreier equation. And for TB0, it is 12.722, and for TB5, it is 14.792. The average crystallite size of the terbium sample was found to be increased. So the lattice parameters of the samples were calculated using despacing equation. The lattice parameters and the average crystallite size of the samples are presented in the table. Standard values as per the JCPDS file is also given for comparison. A slight change in the lattice parameters value is noted due to the incorporation of terbium ion. Then these are the EDAX spectra of the prepared samples. It reveals the elemental composition of the synthesized sample TB0 and TB5. The EDAX spectrum of terbium-0 confirms the presence of lanthanum, tungsten, and oxygen. Next slide, please. No other elemental peaks are seen in the spectrum, which indicates the purity of the prepared sample, whereas the peaks of terbium ions could be seen in the EDAX spectrum of the doped sample, providing a confirmation for the terbium doping. Surface morphology of samples were analyzed using scanning electron microscopic images shown here. Differently shaped particles are seen in the images, and agglomeration of particles are also evident from these images. So the incorporation of terbium ions may be promote the particle aggregation and the growth of irregular crystalline grains. So we can say that doped sample exhibit more irregular shape and size as compared to the pure sample. Next. Then move on to the optical studies. Firstly, UV visible absorption spectroscopy. The UV visible absorption spectra of pure and doped samples were taken to study the effect of terbium doping on the optical property of lanthanum tungstate nanoparticles. That is shown here. Both the sample exhibit a broad band around 240 to 260 nanometer range, which corresponds to the oxygen to tungsten charge transfer transition in WO4 2-. Another band around 320 nanometers observed in the doped sample corresponds to the transition in terbium ions. And the absorption edge of the doped sample is slightly shifted towards the higher wavelength region, which attributed to the photoexcitation from valence band to the conduction band, and also the creation of defect structure due to the terbium ions occupy lanthanum tungstate matrix. The optical band gap value of the samples are calculated using top plot. The calculated band gap values are given in the table for TB0. Next slide. For TB0, it is 4.13 electron volt, and for terbium-5, it is 3.06 electron volt. So the incorporation of terbium ions in the lattice may cause more structural disorder and distortion, which is evident from XRD result too. And due to the presence of these distortion and disorders, band gap value reduces. Then next is photoluminescence studies. The PL spectra of both the samples were shown here. The PL spectra of the the PL spectra of terbium-0 is shown in black line, and the terbium-5 is in red color. And the PL intensity of terbium-0 is very less as compared to the terbium-5. So in order to make a more understanding about the nature of spectrum of terbium-0, it is enlarged and shown in inset. PL spectra of pure sample show a broad feature with a maximal value at 441 nanometer, which corresponds to oxygen to tungsten charge transfer transition within the WO42- group. And the doped sample spectrum has 4 strong emission lines, which are attributed to the transition from the D54 level of the terbium ion. The 4 emission peaks of terbium ions are observed at, next line, please. The terbium ions are observed at 496, 545, 587, and 622 nanometer, corresponds to D54 to FJ7 transitions respectively. Next, please. The emission peak intensity of and the peak positions are peak position and also the color region are given in the table. Here the emission peak intensity of the green peak at 545 nanometer is about 5-fold that of blue or red. So the terbium ions are used as green emitters in the doped substances. Next, ma'am. CI chromaticity diagram. CI is a standard color matching reference which helps numerically to identify a color. Chromaticity of a color is specified by the chromaticity coordinates X and Y, which is calculated from PL data. And the calculated chromaticity coordinates are shown in the table and are pictorially indicated in the CIE index diagram. And the terbium-0 sample shows a greenish blue emission, and the terbium-5 shows a yellowish green emission. Due to the incorporation of terbium ions into the lattice, the color of emission changed from blue to green region. Next. In the table, the XY coordinates are shown, and we can say that the color tuning is possible by adding the proper concentration of doping ions into the host lattice. Next, ma'am. Then here are the conclusion of my study. About the structural studies, the XRD patterns revealed that all structural peaks are well matched with the scheelite type of monoclinic lanthanum tungstate. Due to terbium inclusion, main peak position slightly shifted to the higher diffraction angle values. Both the samples exhibited irregular size and shape. The presence of terbium ions promote the particle aggregation and growth of more irregular crystalline grains, which is evident from some images. IDAX spectra confirm the elemental composition and purity of the sample. And about optical studies, from UV visible absorption studies, it is clear that both the sample have absorption band in 240 to 260 nanometer range, corresponds to oxygen to tungsten charge transfer. And the doped sample exhibit a band around 320 nanometer, corresponds to the transition in terbium ions. And the incorporation of terbium ions cause more structural disorder, which reduces the band gap value. The doped sample has 4 PL emission, intense emission lines, which are attributed to the transition from D54 level 2 of the terbium ions. And the strongest emission spectra of terbium is at 545 nanometer. Due to the presence of terbium ions into the lattice, the color of emission of sample changed from blue to the green region. So the terbium ions can be used as a perfect green emitter in the doped substance. And the terbium doped lanthanum tungsten nanoparticle synthesizer is suitable for UV light excited LED application.
Thank you. It's a nice work. Congratulations. So what is the significance of this photoluminescent studies? What is the significance of this photoluminescent property?
Photoluminescent property, actually, lanthanum tungstate is known as a best host material in the tungstate family for the PL emission. So many literature reports are already there for the europium doping, dysprosium doping studies. So by the proper loading amount, we can observe more intense emission peaks. Basically, tungstate gave a broad emission band. Suppose we can change the emission color by using these rarer ions doping into the host material lanthanum tungstate.
Okay. One technical question: how are you getting these chromaticity diagrams? So you make the fluorescence measurements and then plot it, or what?
Yes, sir. Basically, chromaticity diagram, there's a software among with us, and we first of all we
What
calculate.
data your input? What is your data of input?
Data input is obtained from the PL data, and first of all calculate the X and Y chromaticity coordinates from these data.
Okay. Okay. Thank you. Thank you. Thank you.
Sir. Thank you, sir.
Okay, we can go for the next.
Is that audible?
Yeah.
Okay. I'm Hisna Pierre, research scholar at the Department of Physics, University of Calicut, doing research under the guidance of Dr. P.P. Pratibnan, Senior Professor, Department of Physics, University of Calicut. And the presentation entitled is the enhanced output voltage of T-di-adsorbed cellulose-based triboelectric nanogenerator in novel energy technology. The outline of my presentation includes introduction, experiment, result and analysis, conclusion, and references. We know that we are using many small electronic devices. For that small electronic devices, to power up such devices, we need batteries. But the periodical replacement of batteries and disposal and the material used for the fabrication of batteries are highly hazardous to human life as well as the environment. So we need a solution for that. If we can scavenge the unutilized waste energies from the environment to useful electrical energy, it would be a great solution for the usage of for power up the small electronic devices. For that, we are using nano generator. In nano generator, mechanical or thermal energies are converted into useful electrical energy. There are three types of nano generator. One is pyroelectric nano generator, piezoelectric nano generator, and triboelectric nano generator. In pyroelectric nano generator, waste thermal energy is converted into useful electrical energy. In piezoelectric nano generator and triboelectric nano generator, mainly mechanical, low frequency mechanical energy from the environment is converted into useful electrical energy. Now I am concentrating on the triboelectric nano generator, which is invented by Zhong Lin Wang in 2012, which is based on the coupled effect of triboelectrification and electrostatic induction.
friction. Triboelectrification. Tribo, it's a Greek word which means friction or contact. When two dissimilar material come into contact or come into friction, there would be a generation of charges. That charges is called tribo charges. And as we know, electrostatic induction, when an charged body come near to the uncharged body, the uncharged body get induced some charges. That is called electrostatic induction. Both these triboelectrification and electrostatic induction are nothing but our everyday static electricity. Why we need tanks? Because it converts waste, unutilized mechanical energy like human motion, wind energy, even our breeze can be converted into useful electrical energy, which is an eco-friendly, and it have high efficiency at low frequency, which is low cost, portable and lightweight. Moreover, they have multiple mode of working mode and diverse stores of materials. And I said that there is a diverse choice of materials, so we have to rank such all the materials in order to gain or lose electrons as a series. That series called triboelectric series. In the series, the above materials are called tribopositive materials because it have the tendency to donate electron, and the bottom materials is called tribonegative materials, which have the ability to gain electrons. In my work, I used paper, cellulose paper as the tribopositive material and polypropylene as the tribonegative material. And I said that there are different modes of operation. There are 4 fundamental modes of operation. One is contact separation, relative sliding, single electrode, and freestanding mode. Here the green and blue are the triboelectric materials. When these two triboelectric materials come into contact, the tribonegative material become negatively charged and tribopositive material become positively charged. When these are come in contact, that respective tribo charges will generate, and as they separated, respective opposite charges will be induced on the electrodes. These yellow ones are the electrodes placed on the above and below the triboelectric materials. And due to the disturbance in the electrostatic potential and the electron distribution, the output current will be flow through the outer circuits. This is the main principle behind all these 4 fundamental modes of operation. In my research work, I have used this freestanding mode of vibration. Next is experiment. The materials I used are the T-dye adsorbed bond paper, polypropylene sheet, and aluminum foil. Why I used bond paper? This is a cellulose paper. Bond paper is a biodegradable, rich in cellulose content, good absorption ability, and thicker. Since it is thicker, it can withstand many mechanical excitation. And since it is contains cellulose contents, it acts as a tribopositive material. To enhance the tribopositivity of the bond paper, cellulose paper, I coated the T-dye on this cellulose paper since it contains phenolic hydroxyl group, carboxyl group, and amino groups. These functional groups enhances the tribopositivity of the cellulose paper. As a tribonegative material, I used polypropylene sheet, which contains methyl groups. This methyl group have the tendency to withdraw electrons as compared to the cellulose paper. As an electrode, I used aluminum foil since it is easily available and cost effective. From the materials chosen for the experiment, we can conclude that it is a simple, cost effective, and easily manufactured triboelectric nano generator. Next is working of triboelectric nano generator. This yellow one is the polypropylene sheet. Beneath this polypropylene sheet, I pasted the aluminum electrode, and above this T-dye adsorbed cellulose paper is slided over this polypropylene sheet when I apply tangential force manually. And this T-dye adsorbed cellulose paper act as the freestanding triboelectric layer. As it moves from left to right or right to left side, there would be an disturbances in the electronic distribution in the electrodes, aluminum electrodes. As a result, the output current, output voltage flows through the outer circuit. As a result, we get alternating output. The result of this triboelectric nano generator is measured using DSO. For a bare cellulose paper, the voltage obtained, the output peak-to-peak voltage obtained is almost approximately 3 volt. Whereas when I used the T-dye adsorbed cellulose paper as a tribopositive layer against the tribonegative polypropylene sheet, I got the output peak-to-peak voltage almost approximately 6 volt. So there is an enhancement in the output voltage 2 times. Next is from the introduction, I said that we can use it for small electronic devices. So I experimented it for the load performance of the two LEDs. For self-powering of LEDs, the output from the tank is connected to bridge rectified in order to rectify the alternating current, alternating output voltage, and then it is directly given to seriously connected 12 LEDs. The output, when I applied the mechanical force on the triboelectric nano generator, electrical output is generated. That electrical output is driven these 12 LEDs, and this photograph shows the 12 white LEDs driven by this nano generator. And next is characteristic of commercial capacitor. The output from the triboelectric nano generator can be stored in the capacitor for the further usage. When I used the cellulose paper as a bare cellulose paper as the tribopositive material, within the 70 seconds, I got only less than 1 voltage storage. And when I used T-dye adsorbed cellulose paper, within 70 seconds, I reached to 2 voltage of electrical energy. And as the capacitance value increases, the time taken for the storage also increases. Next is the conclusion. I explained the triboelectric nano generator and its advantages over other nano generator. From the material used and the fabrication method, we can conclude that the fabricated triboelectric nano generator is simple, low cost and eco-friendly one, and which can be fabricated by easy method. The low output load performance of the triboelectric nano generator is done by using 12 commercial LEDs, which can be the tank can be driven 12 commercial white LEDs, and it can be charged 1 microfarad capacitor in 70 seconds to 2 volt. This is references, and thank you, sir.
Thank you. It was a novel type of work, and congrats.
Thank you, sir.
Towards the end, so is it just do you think that this will have a commercial application towards the end?
Yes. Yes, sir. Yes, sir. It should have. There are so many purposes related to triboelectric nano generator, and they are used for the small electronic devices. And not only in the for small electronic cases, they are using a sensor also.
So, what are the other materials used so far for making these triboelectric nano generators already?
My material, I chosen the T-dye. It is a
No. Yours I understood, but what are the other materials which are used?
In the triboelectric series, we have so many materials. We can choose any of any tribopolarized, oppositely tribopolarized material for this triboelectric nano generator.
Such reports are available?
Yeah. Of course, sir.
Then,
but my material is novel one. So far, no one is introduced such T-dye adsorbed triboelectric nano generator.
Okay. How did you maintain the mechanical energy?
Now I use since I need to sense the human mechanical force, I used the mechanical energy by me itself.
Okay. Okay, thank you.
Okay,
Thank you.
Thank you, sir. Thank you, ma'am.
So finally, we come across last presentation. Yeah.
Ma'am, is it visible?
Yes.
Okay, fine. Good evening, all. Myself, Vishak V. Mohan, PhD Research Scholar, Department of Physics, University of Kerala, Karyavattam, Trivandrum. This is our latest research work regarding lab-to-land approach in sort of supercapacitors under the guidance of Dr. Ragi RB, Principal Scientist, CSIR, NIST, Trivandrum, and Dr. Maniraj Mohan. He is our co-author. He is from Kerala Technology, Bangalore, Karnataka. So these are the main contents. So why we are using supercapacitor? Actually, we have batteries, then why we are moving to supercapacitor? Batteries have high energy density and a wide potential window, but the main drawbacks of batteries are its cost, high weight, lifespan is comparatively low, safe operation is not possible, charge speed is comparatively low, and materials are highly costly and not at all eco-friendly. In the case of supercapacitors, the main drawbacks are energy density and a potential window. So in this work, we have try to increase the energy density and the potential window by using commercial mass loading of electrode material, by introducing the commercial mass loading of electrode material. And other positive things are its lightweight, cost is comparatively low, lifespan is high, safe operation is possible, power density is much very high. This is the main advantage of supercapacitor over batteries. That is, charge speed is comparatively high, and a wide variety of materials are possible for the fabrication of supercapacitors. So, by coming to aim, to improve the energy and power density of supercapacitor, commercial level mass loading of 2D materials for practical application through vacuum-free deposition techniques, to design devices with a wide potential window and having high stability. So we know that supercapacitors are widely used in transportation systems. Supercapacitors are used in startup mechanism for automobiles. Due to its very fast charging and discharging properties, supercapacitors make a great tool for regenerating braking vehicles. They are used in electric vehicles to extend the life of batteries. Actually, this technology was adopted by Tesla and Toyota in their latest model cars. And the supercapacitor provide both power in stop, go and go vehicles, example buses and trains. Supercapacitor are used to power emergency systems in aircraft, that we already know. So working of a supercapacitor consists of two electrodes and a porous separator and an electrolyte. Up to by knowing its mechanism can be divided into two double layer capacitors and pseudo capacitors, and a combination is called hybrid capacitance. Hybrid capacitor. The main equation for calculated specific capacitance is shown here: 2I by m into delta V by delta T. I is the current and delta V by delta T is the scan rate by potential, and m is the mass loading. Here we can see that m is in denominator, because that's why when we are increasing the mass loading, the capacitance will decrease. From this equation, we know that if we are trying to increase the mass loading, the capacitance will decrease. But for commercial application, the mass loading should be high. So in this work, we are trying to maximize the mass loading and maintaining the capacitance. So the material we chosen is 2TWS2 because it has higher theoretical capacitance and high surface area, and it is an analog of graphene, and a 2D electron-electron correlation among W atoms, which can enhance the planar electric transport. So these are the materials used for the synthesis of WS2, and a hydrothermal method was adopted for the commercial mass loading of 2D WS2. This is the schematic picture. So by coming to resultant discussion, figure A shows the XRD, B shows the Raman, C shows the band gap analysis, and D shows the FTR. And XRD external phase of WS2 are confirmed, and Raman analysis shows two major peaks confirm the in-plane and out-of-plane vibration of WS2. WS, and the band gap shows an 1.72 EV, which ensure the presence of few layers of WS2. And the BET surface analysis shows that the material having a highest surface area of 28 meters square per gram. By coming to FSM analysis, A and B shows a novel flower-like morphology, and C shows the EDAX spectrum, where W and S presence of W and S were confirmed. No other impurity phases were observed. And by coming to D, it shows the TEM images, a nanosheet-like morphology was confirmed from TEM analysis. So by coming to electrochemical analysis, first we are for a lab scale we have used KH and electrolyte, and check the A shows the CEV and C shows the GCD. These are the two parameters that depends upon the capacitance and the behavior of the supercapacitor. The CV shows that a quasi-rectangular shape, which results the pseudo-capacity property of the material, and the GCD also a nonlinear behavior shows the from the rectangular shape. From the triangle shape, that's also ensure the presence of a pseudo-capacity behavior. The capacitance was calculated, which is around 205 farad per gram at 5 milliwatt per second over the mass loading of 30 mg per centimeter square. So by coming to impedance analysis, the solution resistance is only 0.7 ohm, and charge transfer resistance is less than 1. That means 0.28 ohm, which shows the better conductivity of the material, and the device shows an excellent power density of 0.8 kilowatt per gram and energy density of 14 watt hour per gram. And over that large 10,000 cycle, it shows 100% stability. The percentage contribution is showing both the presence of EDLC and pseudo capacity. So this is the literature among WS2. We have reported the highest specific capacitance of WS2 over higher mass loading. And this is for commercial application. We have chosen an organic electrolyte. And here I have gone from 0.8 volt to 1.5 volt potentiometer. There is no much difference in peaks in both in shapes and the characteristics that ensure the stability of the material. And the impedance spectroscopy also shows the RS value is 3.4 ohm and RCT value is only 1.2 ohm, and the capacitance has reduced to 168 farad per gram. Actually, this is the highest reported value, highest reporting value of a WS2 material in organic electrolytes, not only in WS2 compared to other materials. Also, this is the highest reported value in 30 mg high mass loading condition. So by checking with the previous commercially mass loaded devices, we are on the top. So application, just 1 second charging, a single LED will leads up to 10 minutes, and with a 45-second charging, 8 LED will continuously lead its power up to 5 minutes. So this is a single LED, just 1 minute, 1 second charging. The single LED will leads up to 10 minutes. This is the time showing. And we have fabricated, we have designed a toy car using this supercapacitor. I will try to play the video. So with the collaboration with the startup mission, we are trying to fabricate a supercapacitor for IoT enabled application for rural areas. And these are the summary and conclusion. Pure phase of WS2 nanoflow like morphology synthesis were one-step vacuum-free technique. Fabricated commercial level mass loading of 2D WS2 electrode material. This is first time reporting. Offers a high specific capacity of 205 farad per gram at 5 milliwatt per second, which is greater than previously reported WS2 based device. And also in organic electrolytes, we have reached 168 farad per gram at 1 ampere per gram current density, which is also first time reporting. Both devices shows 100% stability over large cycle, that is 10,000 charge discharge cycle. This is our team, and this is the teamwork. So the friends, acknowledgement, thanks for STAM23 and their coordinators, and all support from the different universities from India and abroad India, and the government of Kerala and the government of India. Special thanks to CMET, ISER, and the CSI and NIST. Thank you.
Thank you. It's a nice presentation, nice work. Congrats.
Thank you, sir. Actually, this is we are going for a patent. That's why some logos are over the pictures. CSI and
Okay,
NIST.
okay. It's okay. Okay, how many are working with you?
Actually, we are 4 members working in super capacitor, and 2 of them are working in batteries, and one is working in latest air electrode batteries.
Okay.
And also sensors and photocatalysis is also started.
Anyway, nice work. Congratulations.
Thank you, sir. Thank you.
Most of our presentations as well as the work were good. Also, I thank MA College for giving me an opportunity to evaluate the work presented by the research scholars of various organizations. Thank you very much.
From my side too, thank you for inviting me to evaluate the sessions, and most of the presentations were really informative and real good efforts from the young future scientists. Congratulations to all. Thank you.
Okay, thank you.